10 to the minus 2, 10 to the minus 4. This gray dashed line is showing when the binary becomes a hard bound binary. And then these blue lines show the time to merger by gravitational waves alone. So this top blue line is when it would take about a Hubble time for these binaries to merge. And this bottom blue line is when gravitational waves will drive the binary to merger within about a year. So we want to put gas disks around these binaries, but if the binary is sufficiently massive or far apart, you actually can't put a gravitationally stable disk around the binary. The disk, at least in some steady state models, will be self-gravitating. And then when the binary gets close enough together, the orbital decay due to gravitational waves will actually be so fast that the disk will run away from the inner edge of the circumbinary disk. So the disk can no longer viscously keep up with the binary, and the binary will, what we say, decouple from the circumbinary disk. So when we think about these circumbinary accretion scenarios, we tend to think about disks in this kind of intermediate range between when you form a hard binary and when the binary eventually decouples from the circumbinary disk. And for the massive binaries up here, we would want to model these with self-gravitating disks, a little bit like we heard about yesterday. But for my talk today, I'll kind of be focusing down in this region where we can have a gravitationally stable disk around our binary. So in kind of the general picture, we imagine gas comes in from large radii with some angular momentum. It's radiatively efficient, so it radiates away its vertical pressure support and collapses into a geometrically thin, rotationally supported accretion disk. And then we treat this disk as just kind of a typical alpha disk where we pick some value for alpha, about 0.1. We prescribe some thickness of the disk, also about 0.1 generally. And because it's radiatively efficient, we tend to treat the thermodynamics isothermally. And then when you do this, you get a situation that looks like this. So this is an equal mass binary fixed on a circular orbit. And you see that this binary carves a deep depleted cavity in the disk. But despite all the symmetries in your problem, you see that this disk actually becomes both lopsided and eccentric. And this cavity actually precesses around the binary about once every 100 to 300 orbits. And then you also see that there's a development of this kind of m=1 lump feature in the edge of the disk that also goes around about once every 5 binary orbits. And then on dynamical times, this disk forms streams that move material from the circumbinary disk onto each of the binary components, where they fall into circumsingle disks, or what we like to call mini disks, that then feed the black hole at the center of these things. So even though this is a very simple setup, it's nice because it's also scale-free. You still get kind of all of this structure in the problem that can give you interesting orbital evolution and possible variability signatures. And then when we do this, what we want to measure is we measure the accretion rate through the disk and onto each of the binary components. And then we want to measure the flow of angular momentum through the disk and then the exchange of forces between the binary and the disk. So for this kind of fiducial setup that I've explained here, the community kind of generally agrees that what you find is if you measure the angular momentum flow through the disk and onto the binary, you find that the disk is actually delivering angular momentum to the binary. So this is showing angular momentum currents in the disk, and this red line is the total angular momentum current in the disk. And it turns out that it's positive and positive enough that this disk in this fiducial model is actually causing the binary to expand. It's driving the binary apart, potentially inhibiting transition into a gravitational wave-dominated regime where the binary eventually emerges. And then if you look at the accretion rate, where we tend to look at the variability in the accretion rate, and we in order to kind of connect this to variability in the luminosity that you might see in time domain surveys, you see that there is this kind of short scale variability on the orbital time of the binary, but then you also get this longer scale variability at about once every 5 binary orbits associated with that density lump at the cavity wall that tends to overfeed the binary about once every 5 orbits. But among the many things that we can relax in this problem, one of the big ones is that we've fixed the binary on a perfectly circular orbit. But in reality, we don't expect these binaries to always form as circular. We expect to have eccentric binaries, so we want to know what happens when they're eccentric. So we can do the same experiment where now we just put an eccentric binary in our circumbinary disk, and we start to measure the forces on the binary. And if you measure the change in the binary semi-major axis as a function of the eccentricity of the binary, for near circular binaries, again, you find this result that the disk is causing the binary to expand its semi-major axis. But if we're focusing just on these solid lines here, for almost all other eccentricities, the disk is actually causing the binary to shrink its semi-major axis. So it's driving the binary together and pushing it towards a potential gravitationally wave-driven merger. And then you can also measure the change in binary eccentricity as a function of the eccentricity, and you find the emergence of these two equilibrium eccentricities, actually, as I think someone mentioned yesterday. So this gives rise to two populations of binaries. You have ones down here that start very near circular, that have their eccentricity damped by the circumbinary disk. So they'll remain nearly circular, and they'll be expanding their orbits. So the near circular binaries are being pushed apart. But then at any other eccentricity, like if you start at 0.2, you'll have your eccentricity pumped to this equilibrium around 0.4, and if you start really high, you'll have it damped again back to this equilibrium point, where now the gas is helping to drive the binary together and shrink its semi-major axis. And then if we look at the variability associated with these different eccentric binaries, the scale here is a little different than I showed before, but for these near circular cases, you get something that is about sinusoidal with kind of this bigger peak about once every 5 binary orbits associated with the lump. But once you get to an eccentricity of about 10% or 0.25, this 5-orbit variability disappears, so you no longer have the lump. The shape of your variability goes from kind of sinusoidal to much more of like a sawtooth pattern at the binary orbital frequency. And then at very high eccentricity, that starts to really be spiky and kind of flare-like and doesn't really look like a sine wave or anything at all anymore. And then there's some of this other funky behavior that someone can ask me about at the end if we want to get into it. Okay, but so this has all been prograde results. But as I said, we imagine gas comes from large radii with some angular momentum and then collapses into the disk. But because of that, we would expect some of these gas clouds that come in with some angular momentum to eventually settle into stable retrograde configurations with the binary as well. So we can look at these retrograde disks, and dynamically they're kind of interesting because unlike the prograde case at low eccentricity, they no longer have resonances. So for the circular case here, you find that the binary, the system settles to almost a completely perfect steady state solution where this is barely time variable at all. You have this kind of much smaller cavity carved by the binary. You still form these mini disks here, and then some material that gets redirected through the domain center forms this standing kind of accretion bridge. But then as you go to higher eccentricity, you again start to pick up some structure in the circumbinary disk. So the binary starts to pump these circular waves into the disk once every binary orbit. Around apocenter, the mini disks tend to get partially disrupted through kind of collisions with some of the impeding circumbinary material. And you start to see some of these interesting behaviors. So if we do the same kind of experiment where we look at how the semi-major axis of the binary and the eccentricity changes as a function of the binary eccentricity, we get less structure than in the prograde case. But this is still very interesting because the in-spiral rate of the binary here due to the disk is about twice to 5 times as fast as in the prograde case. And then we no longer have stable eccentricities. So for all eccentricities in retrograde disks, you're going to have your eccentricity pumped. So this is just going to continue to pump and pump and pump eccentricity into the binary until it potentially facilitates a merger. So one of the interesting things we can do is we can just integrate through this and ask, what is the maximum eccentricity that this retrograde disk can impart onto the binary before gravitational waves kick in and start to circularize the binary. So when the gravitational wave circularization becomes faster than the eccentricity pumping in the disk. And depending on where we start our binary, you can get really, really extremely, so these are possible Lisa sources, you can get really, really extremely eccentric binaries, many, many, many nines here at the end. So it means that a possible signature of these retrograde accretion phases would be not only eccentric mergers in the Lisa band, but that might also come with a negative spin parameter or chi-effective spin parameter because the disk will be spinning the binary to have opposites, or the components to have opposite spin than the orbital angular momentum of the binary itself. Okay, and then if we look at the variability from these retrograde scenarios, we see that near circular you have almost no variability because you're in this steady state. But at low eccentricities, it's a nice sinusoidal variability for the most part that only varies on the orbital period. But then at large eccentricities, this bifurcates into kind of a 2-period variability where you have a big peak followed by a small peak and a big peak and a small peak that at really high eccentricities can really become a strong flare and then a small peak and a strong flare and a small peak. And this might be due to the fact that at high eccentricities it's actually possible to get some of these resonances in retrograde scenarios. So someone can ask me about that later if they want. Okay, and then the last thing I'll say before I wrap up, going back to prograde disks, is we've talked about some of the changing orbital elements of the binary, so how it's accreting, how it's changing its semi-major axis, how it's changing eccentricity. But the other thing that the disk can do is it can actually cause the binary to precess. And people haven't measured that before in these simulations. So what we did is we just went back, and this is the same data I showed at the beginning, where this is the eccentricity, the change in eccentricity as a function of eccentricity, change in semi-major axis. And this black curve now is how the disk is causing the binary to precess. And we see that this is actually about an order of magnitude faster than the change to the other orbital elements of the binary. And so this is the prograde scenario, and then we can also, for fun, we can measure this from our retrograde experiment. And we see that it's generally similar. At low eccentricity, it's about a factor of 2 larger. And then at high eccentricity, it tends to be about similar. And then we can ask, or we can try to get a handle on how this might matter for electromagnetic and gravitational wave observations by comparing this precession rate to the precession you get from general relativity. So these lines here are showing where the disk precession is equal to the precession from general relativity as a function of mass and separation, where in these shaded regions, disk precession is dominating, and in the white regions, gravitational or general relativistic precession is dominating. And then this black line is again showing our decoupling radius, where the binary will decouple from the circumbinary disk. And then we're showing 2 different values of the disk mass. So here the disk is about 10 to the minus 3 times the mass of the binary. Here it's equal to the mass of the binary. And for gravitational wave sources, we can put some merger times due to gravitational waves that would be relevant for something like LISA here. And we see that this precession effect can dominate all the way down to decoupling and to binaries that are a month or even a day away from merging. So these massive disks could potentially induce significant dephasing into a gravitational wave signal that gets measured by LISA. And then for electromagnetic signatures, if we put some periods on here that are something like periods that we might be looking for with LSST or in time domain surveys, we see that even at these less massive disks, you can get precession effects from the disk that might actually be important for your observational model if it depends on an orbital reconstruction. So something like a flaring model where every time the binary passes in front of the other, you get a lensing flare. In order to accurately time this thing, you might actually also need to include corrections for the precession due to the circumbinary disk. So I think I will stop there and say that we expect many of these binaries to undergo gas accretion phases, can have important implications for the orbital evolution and what we might observe, and I can take some questions.
So, question for Christopher?
For your E equals to 0 case, there's an asymmetry of the circumbinary disk.
Mm-hmm.
Is that from precession or?
In the retrograde or the prograde?
I think prograde. One of the earliest.
So for the circular binaries,
yeah,
the eccentric disk.
Yeah.
And what was the question about it?
Sorry, not circular, and then the disk is asymmetric. So maybe it's on your conclusion slide actually.
Yeah. I don't know how to bring it back up. Yeah.
So you're saying at some part of the orbit the disk is closer to the black holes.
Yeah.
Is that from precession?
No, it's just that the disk is eccentric and kind of lopsided compared to the binary, so it always kind of feeds from this close side. But then it does precess around as well.
Okay, but this is a circular.
This is a circular binary, yeah.
Circular case, okay.
Mm-hmm.
And in the eccentric case, it kind of, I guess, counteract that effect?
Yeah, so in the eccentric case, you get these interesting state transitions in the disk, actually. So you're right that here, for intermediate eccentricities, the disk is actually no longer eccentric. And we think this is connected to why we see this behavior and the emergence of these equilibrium eccentricities. And we're still trying to connect the two, but you're right, you do. So circular, you see an eccentric cavity, but then for an eccentric binary, the disk
who is Matteo Bonetti from University of Milano Bicocca. Thanks.
Loading.
And maybe I can remind you, when asking question, we can tell our name before.
Don't know. I don't know. Maybe you can try with your laptop because it's strange. Yeah. Oh, okay. Okay. Seems to work. Exactly. Okay. So, hi everyone. I'm Matteo from Milano Bicocca. And in this talk, we present a recent work about the quasi-periodic eruption that may be caused by extreme mass ratio in spirals. So this work is done in collaboration with all these people here, and particularly Alessia. So, quasi-periodic eruptions. So this phenomenon, QPs, are fast bursts in the X-ray soft band that are being discovered very recently. And they are essentially repeating every few hours, superimposed over an otherwise stable flux around a low mass massive black hole, so around 10 to the 5, 10 to the 6. And they are quite peculiar because they are quasi-periodic in the sense that they repeat every few hours, but every burst arrives in a little bit in advance or in delay with respect to the others. They have thermal-like X-ray spectra in this range here. The duration of the peak is around to 1 to few hours, maybe half an hour. They are quite bright because the peak luminosity is 10 to the 42, 10 to the 43 ergs per second. So this is not a quasar, but still this is an impressive luminosity. And they have been observed with many observatories from XMM Newton, Chandra, Swift, NICER, and eROSITA. So GSN 069 is the first QP sources that have been detected. That is, it's quite peculiar, I would say. So in this source, you can observe this bolometric-like curve that resembles something like a TDE. So probably there is a connection among QPs and TDEs, but we still don't know. And as you can see, QPs generally appears when the bolometric flux is lower. So the source is peculiar in the sense that they first observed this long decay from this putative QP source, and they detected the QP in the X-ray band. And then at some point, there also have been a rebrightening. This was unexpected, of course. So this maybe could be a partial tidal disruption with a repeating. So there is another passage and another stripping material on the massive black hole. But this is all, everything is theoretical. And the peculiar thing is that when the bolometric flux increases, QPs generally disappear. And in fact, here you can observe the X-ray observation of QP. So you can see that they are quite sharp peak, and they are quasi-periodic. And these are consecutive observation. And when the flux has rebrightened, QP started to disappear in this regime here. So here we don't have any QP, here we have QPs, and as soon as the flux has started to go down, then QP has reappeared. So probably is something connected with the flux of the QP that has been masked by the high flux of this secondary brightening. But this is only one source, this very specific source. There are other 3 of them that have been confirmed. So we have Eero QP1, Eero QP2 that has been discovered by eROSITA, of course, and then follow up with other observatories. And then there is this other source that is very strange, RxJ. So up to now, we don't have a really confirmed idea of what QP are causing by. So a lot of models have been proposed. For example, the tidal stripping of the helium envelope of a massive star, white dwarf from highly eccentric orbits. So in this case, the white dwarf is filling up the Roche lobe and then is transferring material to the central massive black hole. Another possible model can be the stable or unstable mass transfer from main sequence stars. Also, multiple extreme mass relation spiral interacting among them has been proposed, like in this model here from Metzger. But here, and all this model here assumes that the X-ray emission is generated by the accretion on the massive black hole, so the primary massive black hole. Another possible model is that this X-ray emission can be generated by the impacts of a low mass companion that is orbiting around the primary that is crossing the accretion disk of the primary massive black hole. This is what I'm going to present. So our model setup is the following one. So we have the primary massive black hole with this spin in this direction. Then we have a secondary massive black hole that is much smaller. So the primary is around 10 to the 5, 10 to the 6 solar masses. We choose here 10 solar masses just for explore our modelization. In addition to that, we also consider a misaligned disk that is also precessing. And this is why we said that quasi-periodic eruptions are actually quasi-periodic. And this quasi-periodicity can be caused by the combination of the different precessions. So we have the relativistic precession, the apsidal relativistic precession, so the relativistic precession of the pericenter. Then we also have the relativistic precession due to the spin of the primary massive black hole. But if the disk is also misaligned, also this disk can precess and add another periodicity in the game. So since we are very close to the massive black hole, we need to use post-Newtonian correction. So we consider the post-Newtonian correction up to 3.5 post-Newtonian order plus the leading order spin-orbit coupling, just to model the effect of the spin. For the precessive disk, we consider it as a rigidly precessing body, and we know that in some situation this is actually the case. For example, if the disk is sufficiently thick and sufficiently narrow, so further to being much more easier to model, there are situations in which this kind of disk can exist. The disk precession in this case can be, the period of the disk can be around 1 to 100 days. So this is something that can be compatible with what we are going to observe. And the next thing that we have to model is the emission from this kind of system, because if we model the dynamics, we can have, let's say, a description of the timing of these QPs, but then we have to figure out how to get to the 10 to the 42 ergs per second. So in our scenario, we consider that the emission is generated by the gas that is pulled out from the disk when the secondary black hole enters the disk. Okay. Then this the gas cloud expands and cools down, and the emission is generated by the black body radiation that is emitted by this thick cloud that is pulled out from the disk. Okay. So to get this kind of luminosity, we need that the initial clouds is something around 10 to the 11 centimeters. And we can get this by considering the influence radius of the secondary massive black, so the secondary black hole that is orbiting the primary one. The influence radius is essentially Gm, the mass of the 100 solar masses. And then at the denominator, we have to consider the sound speed, but also the relative velocity with the disk. So here, this is something important, because in many works, this velocity here is considered the Keplerian orbit around the primary black hole that at few hundred gravitational radii is, I don't know, something like 50,000 kilometers per second. So you get an influence radius that is very small. But you need to consider that you are moving within the disk, so the relative velocity is much smaller, okay? So if we start with a cloud with this initial radius here, then we assume adiabatic expansion, and then during the expansion, the temperature drops, and so the peak of the black body shifts at lower temperature and slowly exit the X-ray band, okay? So during the shock, we assume that the temperature increases using the Rankine-Guyon conditions. These ones that are related to the Mach number. And we essentially compute the luminosity by essentially integrating the black body flux in the 0 to 2 keV band. And we assume that the temperature decreases with this very simple law here. So I said that we consider a 100 solar mass black hole. Of course, this is our choices for our modelization. We just wanted to explore the situation. And we excluded other possible perturbers of the disk. For example, other compact objects like neutron star and white dwarfs, they have a too small mass for an influence radius big enough. And of course, if we consider their surface is too small to produce a cloud that is large enough to produce the luminosities. Black hole much smaller than 100 solar masses for the same reason cannot produce the required luminosity. If the black hole is much larger, then the gravitational wave spiral time can become too small to explain the QPE that we are observing. A lot of models consider that actually stars are crossing the disk, generating the luminosity. Stars are large enough to produce a cloud that is big enough to produce the luminosity, but stars can get tidal disruptions, and in fact, in 3 out of 4 of the sources that we are considering, the tidal radius is large enough that the stars can be destroyed in 1 or maybe few pericenter passages. So stars can get destroyed very easily. Otherwise, they can also overfill their Roche lobe and lose material. And also, you know, at every passage, you are crossing a disk with velocities that are several thousands of kilometers per second. And so stars at some point can get stripped every passage in the disk, and so the QPE cannot last forever in this case. So that's why we are going to consider a black hole that does not have this kind of problems. Okay, so we just put everything together in our semi-analytical model, and then we just try to reproduce the light curve of the QPE that have been observed. And I would like to stress that these are not, so on the upper panel you can see the observations, and in the lower panel, our semi-analytical modelization. I would like to stress that these are not fits of the data, but they are just, we just tune the parameter essentially by eye in order to see if we can reproduce the phenomenology that we see. So for the more regular QPEs that are GSN 069 and Eero QPE2, so they are more regular in the sense that we have an alternation of high and small peaks, and the quasi-periodicity is not dramatically different among different peaks. And so you can see that by choosing these parameters here to describe our system, we can get a timing that is quite well reproduced, and also the alternation of high and small peaks in luminosity. So you can see that we can get the observed luminosity quite easily. For the other 2 QPE sources, the situation is much more messier because, as you can see, the observations are quite complicated. So we cannot reproduce precisely the pattern that we are observing. But for example, here for Eero QPE1, we can reproduce this modulation that is overimposed over the single peaks, like this. So you can see something by eye. And probably we think that this can be produced by the precession of the disk. For the case of RxJ, as you can see here, the structure is extremely complicated, and since there are a lot of parameters in the model, tuning by eye is not very optimal, so we need to run a Bayesian inference here to find out the parameters that can best explain this behavior. But I can say that generally this behavior in which we have two peaks very close, they are generally caused by a much more eccentric Henry rather than the previous one that are almost circular. Sorry. As you can see here, the eccentricity is quite small for the other three sources, while for RxJ is generally higher. And we can have this pattern of two peaks much more closer than the others. But as I said, this is very complicated to model. So for the case of GSN069, that is the one that we have explored more, we also explore how the parameters can affect the light curve. So for example, changing the spin, you can see that the pattern modifies. So the gray lines is the standard case that I showed before, and the blue one is the variation of one of the parameters that is highlighted here. So for example, if we also, as I was saying, when you increase the eccentricity, we have a doublets of flares that are separated by a much larger time scale. And if we put a retrograde Emery, because I haven't said, but all these systems here require a quite low inclination, because the relative velocity should be low, otherwise the influence radius is too small and you cannot reproduce this kind of luminosity. So the relative inclination of the disk and the Emery is generally within 10 degrees or so. And in fact, if we change the inclination and we put retrograde Emerys, you can see that the luminosity drops by an order of magnitude in here. Okay, finally, last thing. So this is a semi-analytical modelization, so we just wanted to see if we can get something that is reasonable by running simulation. So we just consider the code Gizmo in its MFM mode. We consider a mass ratio of 10 to the minus 4. We consider a disk with radiation pressure and backbody cooling. And we consider the case of GSN069. And here we implemented the post-Newtonian equation into Gizmo to model the Emery motion. And so here you can see the face-on view of the disk, in which we have 4 passages. So you can see that it enters, and it can create a hole. And there is some ejected material that you can better see in the next slide, if I can manage to go there. Apparently not. Okay, maybe it's this one. Okay, so here you have a slice, and you see that at each passage there is the material that is ejected on both sides. So the perturber is pulling out the material during its motion, but because of the shocks, the gas also bounces back from the disk, and so you have emission from both sides of the disk. Okay, so this is very preliminary because we are still figuring out how to get the light curve from this kind of simulation that is not straightforward, because as you can imagine, the situation is a bit messier. But from very preliminary results, we can see that we can almost reach the required luminosity from the QPs, also from the full hydrodynamical simulation. So this is very encouraging. And so since I finish my time, I can just leave here my conclusions and take any questions. Thank you.
Questions? Okay, let's welcome Kunyang, who is from the Institute d'Astrophysique de Paris.
All right, thank you. I'm Koyang Lee, and I'm a postdoc at IAP France, working with Marta Voluntary and Guillaume Dubois. Please let me know if you can't hear me, because I tend to drop away from the mic. All right, so my current research is on the massive black hole binary evolution in cosmological simulation. But today I'm going to switch gear and talk about my previous study on the detectability and coalescence fraction of kiloparsec scale due AGNs, which I did at Georgia Tech as part of my PhD thesis with Tamara Bogdanovic and David Ballantyne. So observational researches for kiloparsec scale due AGN is crucial for understanding the role of mergers in the evolution of galaxies. And also these objects are very important parent population of merging massive black hole binaries which generate gravitational waves. So understanding population of due AGN is necessary for determining the expectations for future gravitational wave detectors like LISA. However, observations have only uncovered a very small number of confirmed due AGNs, and there are two major difficulties in observing the systems. So first, the small separations between the due AGNs requires a very high angular resolution to distinguish or resolve the source. Second, the significant gas obscuration will actually block the system from our view due to the merger of the galaxy. And there is another set of challenges arise from cosmological simulations, which attempt to model the formation and evolution of due AGNs. And these cosmological simulations often lack the resolution needed to calculate the observational properties of kiloparsec scale due AGNs. And the cost of increasing the resolution in the simulation is just too high. So to solve this problem, we built a semi-analytical model to study the pairing of massive black holes and the detectability of due AGNs. Right. So our galaxy model contains a primary black hole M1, which is fixed at the center of the galaxy remnant, which contains a stellar barge, gas disk, and stellar disk. And our secondary massive black hole M2 orbits the primary in the disk plane, so we're basically looking at a 2D problem in the disk plane. So we assume, in each simulation, we put secondary about 1 kiloparsec away from the primary, and the simulation stops when the separation between them reaches below 1 parsec. And in the simulation, we assume M1s accrete at boundary rates, and we also assume their luminosity does not exceed 10% of the Addington luminosity, just in order to match the typical values found in X-ray surveys of due AGNs. Well, for M2, we assume they accrete at the Addington limited boundary hole Lyttelton rate. And from the dynamical aspect, in the decay process of the black holes, we take into account the stellar and gas dynamical friction. And for the stellar dynamical friction, we use the model from Antonini and Murray 2012, which take into account both the stellar population moving faster and slower than the secondary massive black hole. And for the gas, we use the model from Kim and Kim 2007, which break the locality and take into account the spiral shape of the gravitational wave due to the orbital motion of the secondary and around the primary. And for each simulation, we have 5 key parameters. And by varying each of them in their range of interest, we can build a primary space that give us about 40,000 pair of massive black hole in different galaxy environment. All right. So also observationally, the ability to successfully identify a due AGN, here we're looking at direct image method. It depends on both the separation between the two black holes and also their luminosity ratio, where higher values will increase the chance of detection by the direct image method. So here we're looking at the 2D probability distribution of a pair of massive black hole in relatively low pair mass, low mass ratio, and slow rotating gas disks. And y-axis shows the luminosity ratio, while x-axis shows the separation between the two massive black holes. Well, the color bar represents the probability. And as you can see by the hottest pixel in this plot, that this pair of massive black holes is most likely to be observed as a due AGN with a separation of, sorry if I can move this one. I don't think I can move this bar, but it's saying kiloparsecs. Thank you. So it's most likely to be observed as DUAGN at a 0.4 kiloparsec separation and at a luminosity ratio of about 10 to the -2. And this is the same plot, but for another pair of massive black hole with relatively higher pair mass, higher mass ratio, and fast rotating gas disks. This means basically 80% of the circular velocity. And in this case, you can see by this hottest pixel here that the most likely separation is about 0.7 kiloparsec, and the most likely luminosity ratio is at 1. And both quantities are higher compared to the previous slide, the previous system. So basically, by this comparison, you can see that one of the key findings of this study is that DUAGNs are most likely to be observed in host galaxies with higher pair mass, more comparable mass ratio, and galaxies with fast rotating gas disks. All right, so overall, we expect configurations that leads to long-lived, widely separated DUAGNs with high luminosity ratios to be most detectable by the direct image method, right? So here we So here we, sorry about that. So here we combine the most likely separation, most likely luminosity ratio, and the evolution time that this system spanned at this true value to be the relative detectability of this system of DUAGN. And you can see in this plot, this is the detectability of all DUAGNs in our system, those 40,000 of them. And y-axis is log detectability, while x-axis is the bulge mass and gas fraction. And as you can see in this plot, that DUAGNs in host galaxies with bulge mass more than 10 to the 10 solar masses, or gas fraction larger than 0.2 have the highest detectability, as illustrated in these two right circles. And this is because from the dynamical aspect of the problem, that these systems are, the decay process of these systems are dominated by the gas dynamical friction force alone, while in other systems, the decay process is driven by both the stellar and gas dynamical friction together, which means that these systems are actually taking longer time for them to coalesce, which actually make them shine longer as DUAGN. That's the logic here. And yeah, so these are actually gas-dominated systems that have the highest detectability here. All right, so what happens if we add in feedbacks? So the radiation produced by the accretion onto the massive black hole can actually influence both the dynamic and the luminosity of the system. So first, from the dynamical aspect, as we find in one of our previous research here, that this phenomenon of negative dynamical friction, which is under the radiation feedback, the gas dynamical friction force actually reverse the direction and shrink in magnitude, which makes the pair take longer to coalesce, increase the decay time, that means. And this effect actually increased the detectability of this pair. But on the other hand, we also know that the accretion, the radiation feedback can also regulate the accretion rate of the massive black holes. This is because the thermal pressure of the ionized bubble surrounding the accreting black hole can regulate its accretion rate and make it smaller. But the magnitude of this effect depends on both the motion of the black hole, also the gas density, the gas temperature of the surrounding medium. And in our study, we find that most of the primary black holes, at least in our data parameter space, that they are not affected by the radiation feedback on accretion because the gas density at the center of the galaxy is just strong enough to counter the thermal pressure. But we find most of the secondary massive black hole, they do fall in the regime where radiation feedback strongly suppress their accretion rate. So in summary, basically, the radiation feedback, the dynamical aspect of radiation feedback will increase the detectability of DUAGN, but the radiation feedback on the accretion aspect will strongly suppress the accretion rate, and also the luminosity ratio L2 over L1 makes the radiation feedback in general a negative effect on the detectability of DUAGNs. All right, so this plot basically shows what I said. The top row, you have seen that before. This is the detectability without radiation feedback. On the bottom, you see that in the presence of radiation feedback. So as you can see that the luminosity ratio, it becomes bluer, means it is suppressed due to the suppression of radiation feedback. onto the accretion rate of the secondary massive black hole. And especially those ones, gas-dominant ones, the detectability of them is suppressed the most because gas component is the dominating factor in those galaxies, and also radiation feedback only affect the gas component. And that's why this system, the gas-dominated system, are affected most here in the detectability of DUAGNs. All right, so far we have been looking at MOC, the statistical study of MOC galaxy models, and now we can actually use illustrious TNG data in our semi-analytic model for post-processing. And by doing that, we can actually get a prediction of the massive black hole binary coalescence rate and also generate DUAGN coalescence fraction. So we count the number of DUAGN that reach coalescence before 0, and plot the coalescence fraction of them in the left panel. And as you can see that different curves here, the top 3 curves represent DUAGN with different initial separations. And you can see by the comparison between these 3 that the coalescence fraction decreases as the separation increases and as the redshift decreases. And this is pretty straightforward because when you have larger separation, it's more difficult for them to coalesce, right? And lastly, this right circle curve here is the money curve. It's basically the general DUAGN coalescence fraction for all the DUAGN sample in TNG50. And I will talk about how we can use this later in the slides. And on the right, we have the corresponding LISA detection fraction of the same group of DUAGNs, assuming a signal to noise larger than 8 to be detectable by LISA. All right, so what we can do with that, the coalescence fraction of DUAGN, one example is that we can calculate the DUAGN coalescence rate using that fraction. So here, this is the equation for that, and here F-col is just from here, this coalescence fraction of DUAGN. And N DUAGN is the co-moving DUAGN number density as a function of redshift, while DL is just the luminosity distance. So actually, by using this equation and calculate the coalescence rate of DUAGN, we can actually potentially connect the EM observations and the gravitational wave detections of massive black hole binaries. And that's basically the main goal of this methodology I'm talking about here. All right, since I'm running out of time, this is my take-homes for this short talk. So we basically we develop a semi-analytical model and also the methodology of finding properties of galaxies which are most likely to host observable DUAGNs, and also using the massive black hole pairs data in TNG50 and our model for post-processing, we present this DUAGN coalescence fraction and demonstrate a way to connect between the EM precursors and coalescence, and in the effort of bridging the gap between EM observations and gravitational wave detections. All right, so this is my last slide, and thank you for your attention. And if you're interested in the full picture of our work, you can read them in these papers of mine, and they contain all the details. And if you have any questions, you can email me. But before that, I forgot to introduce, this is my dog Jade and her fellow kitty. And I'm just bringing this picture to brighten up your day. And also because this is a young astronomer meeting, I want to remind all the young researchers that, scientists, no matter how senior they are in their career, they're just human like you and I. So don't be scared and don't hesitate to reach out and talk to people. And who knows, that may just be the beginning of a bright, brilliant science idea, right? So that's all I want to say, and thank you. I'll take any question you may have.
So let's welcome the next speaker, Marko Micic, I think it's pronounced, okay?
That's correct.
From the University of Alabama.
Okay, so hello everyone, my name is Marko. I'm a PhD student at the University of Alabama. And today I'll be talking about dual AGN in dwarf-dwarf mergers. That's the main part of my talk, but I will also briefly talk about dual AGN in minor mergers and AGN in galaxy groups made out only of dwarf galaxies. So dwarf galaxies are the dominant type of galaxies in the local universe. Every massive galaxy contains multiple dwarf satellites. For example, Milky Way contains a dozen of satellites and the number is growing. Also, many simulations and observational work suggest that dwarfs are also dominant across all redshifts. For example, observations of UV luminosity function suggest that regardless of the shape of the bright end of the function, the number of bright galaxies at z greater than 6 is not enough to ionize the universe, suggesting that there is a significant contribution from unseen rich population of ultra-faint dwarfs that dominate the UV luminosity density at redshifts greater than 6. And that even the deepest surveys are only seeing the tip of the iceberg of the populations of galaxies at high redshifts. This implies that in the early universe, the merger rate per unit volume is dominated by dwarf-dwarf interactions, but also the main prediction of lambda CDM cosmology suggests that the growth of structures happens in a hierarchical manner, which means that smaller structures merge to grow to create larger ones, which places dwarf-dwarf mergers at the starting point of the evolution of galaxies. Also, important questions are, do all galaxies contain central massive black holes? How big are those first black holes? What are the first primordial black hole seeds? But we can't answer any of those questions because direct observations of high redshift dwarf-dwarf mergers are impossible because of their faint nature. We can overcome this issue by studying local pairs of dwarf galaxies. If we assume that local dwarf galaxies had quiet merger histories, they preserve information about the high redshift galaxies, that their black holes preserve certain information about the primordial seed. We can use local pairs as a proxy to study the initial stages of galaxy and black hole evolution. There have been some works recently studying dwarf-dwarf mergers in the local universe. The most notable work, the Tiny Titans project by Stierwald et al. Here are 4 types of dwarf mergers from their work. Then Paudel et al. Did a similar research, and Kado Fong most recently studied local dwarf galaxies that are isolated but contain tidal debris, meaning that they have completed their merger with another dwarf galaxy. But the number is still very small. It's only a handful of candidates in all 3 works combined. And the presence of AGN in these systems is very limited. There is only one example of a dwarf-dwarf merger with a single AGN, which is the dwarf-dwarf pair Markarian 709 discovered by Rains in 2014. The upper right image shows the system. At the time, they only had the redshift of the southern galaxy and just assumed that the northern one is associated with the southern one. Follow-up observations with HST and Keck confirmed that these 2 galaxies are associated. Lower left is the high-resolution image showing 2 galaxies connected with the tidal bridge and the presence of an AGN in a southern galaxy, but there is no presence of AGN in the northern galaxy. So why do we have only a few dwarf-dwarf mergers? Because they're faint, they're hard to spot. Most of them often don't have readily available spectrum and spectroscopic redshift, which means we can't calculate physical separation between 2 galaxies. We don't know if they're really a pair or just projected foreground, background pair of objects. On top of that, detecting AGN in a dwarf galaxy is extremely challenging. Dynamical methods are impossible beyond a few megaparsecs, which leaves detecting signs of accretion using X-ray observatories as the only method. However, lower mass galaxies probably contain lower mass black holes, which are fainter in X-rays, often requiring hundreds of kiloseconds to detect them even at modest distances, making this approach not suitable for large-scale searches. So I tackled this problem. My research was just aimed at discovering faint dual AGN in faint mergers that were previously missed by other searches, not necessarily to dual AGN in dwarf mergers. But I collected all deep archival channel observations containing at least 100 kiloseconds of exposure time by merging often multiple observations. And then I went through all of those observations, collected all sources separated by less than 5 arc seconds, which are potential X-ray pairs. I cross-measured sample with WISE AGN catalog because AGN are supposed to create very specific signature in mid-infrared colors just to solidify the AGN presence. And then I studied properties of galaxies hosting these sources, trying to find evidence that the galaxies are actually interacting and that the sources are genuine pairs. In many cases, as I already said, I didn't have readily available spectrum or distance, so I resorted to detecting tidal debris around these galaxies, which would prove that the galaxies are actually associated. Something like Markarian 709 had a tidal bridge connecting two galaxies. Some developed tails or shells, and so on. So I detected 2 candidates for dual AGN in dwarf mergers. First of them is shown here. We nicknamed internally galaxies. We gave them names. So this one is called Mirabilis. It's classified as an Abel 85 galaxy, although the redshift is poorly constrained. The galaxy, this is CFHT telescope image, shows the main galaxy with a long, clumpy tail and a smaller counter tail, creating this rough S shape, which is a typical signature of ongoing late-stage mergers. Assuming that the Mirabilis is actually an Abel 85, its physical properties, such as magnitude and radius, are very faint and small, many times smaller than, for example, LMC, like a local dwarf galaxy. X-ray image of Mirabilis shows 2 sources right next to each other, a separation of around 4 arc seconds, or at a distance of Abel 85, around 4.4 kiloparsecs. We had 3 observations, total with around 240 kiloseconds, and luminosities of a few times 10 to the power of 40 ergs per second. Here is combined image of CFHT, Chandra, and WISE, where purple contours show the locations of X-ray sources. Red star is the location of AGN consistent infrared source, where you can see that one X-ray source resides in the main galaxy while the other resides in the first clump. So this is consistent with a scenario of a late-stage merger where the smaller galaxy has been completely disrupted by the forces from its more massive neighbor, leaving this tail shape behind it. So, as I said, the redshift is poorly constrained, so we need to consider certain different scenarios. For example, what if Mirabilis is a background object, more distant than we initially anticipated? As you move it backwards, its properties increase, its magnitude increases, its size increases. When we compare it to the case of Markarian 709, they have the similar colors, and for Mirabilis to be similar to Markarian 709, it will have to be a redshift of almost 1 because of how small it is, assuming Abel 85 distance. At that distance, X-ray sources are hyperluminous, and the tail is record-breaking long tail. If it's even more distant, then Mirabilis is likely not a dwarf anymore, but then disrupted galaxy is certainly many times smaller. So it's still a dwarf-related merger with record-breaking tail and hyperluminous X-ray sources, which is still very interesting. We also have to consider, because the luminosities are kind of low, although similar to other luminosities of other AGN dwarf galaxies, but still they could be accounted for non-AGN processes, such as presence of hot interstellar medium gas, or population of X-ray binaries and so on. But I'll just briefly talk about this because I have no time for that. We can talk about this later. We find that it's unlikely for the sources to be powered by X-ray binaries or ultraluminous X-ray sources from a statistical point of view. The second object is, we'll name them Elster and Vintule. Unlike Mirabilis, this is an early stage merger where we can see 2 separate galaxies connected with a tidal bridge, very similar to the Markarian 709 case. Better constrained redshift, likely members of Abel 1758 Southern Cluster. Elster is more luminous and larger than Mirabilis, but still its properties are in line with local dwarfs. Vintule was previously uncatalogued before we detected it, and it's smaller and fainter than Elster, so its dwarf nature is even more emphasized. Again, X-ray image of the system. 4 observations separated by 5 arc seconds of around 20 kiloparsecs, and luminosities order of magnitude 10 to the power of 42 ergs per second. Again, combined image. Again, we have WISE X-ray infrared source with colors consistent with being AGN. In both cases, we only see one infrared source, which is because the angular separation of WISE is larger than the separation of these 2 X-ray sources. So even if there are 2 infrared sources, we can't separate them. We are doing right now follow-up observations. So we obtained 2 sets of observations with Gemini telescope. Thank you. These observations will allow us to calculate distance to properly calibrate AGN emission. Work is in progress, and we have very encouraging results for the case of Mirabilis. I can't talk more about that right now. We also obtained VLAA configuration observations at 5 gigahertz with the aim of constructing the fundamental plane of black hole activity, which is the empirical relation connecting the radioluminosity, X-ray luminosity, and the mass of the black hole. Given how small, for example, Mirabilis is, it makes it justified to expect that it's probably powered, its AGN are probably powered by intermediate mass black holes, which would make this a possible dual AGN powered by dual intermediate mass black holes, which would be very, very intriguing discovery. I also want to briefly touch minor merger dual AGN. Minor mergers is when you have 2 galaxies with large difference of masses, but dual AGN in these sources are rare, only a few known, all in late stage mergers, because simulation suggests that the growth of AGN in these systems is mostly not simultaneous. Primary AGN is mostly unaffected by the merger, while secondary AGN is unable to accrete efficiently for the most of the merger. It undergoes 2 brief phases of growth, one in the early stages where the accretion approaches adding to the limit, but it gets abruptly shut down by tidally stripping of the gases from the more massive galaxy. Second phase is once it circulates within the disk of the large galaxy and starts consuming the gas reservoirs. However, even though those phases are brief, it's expected that in some cases the secondary AGN can increase its mass by a factor of 10, which is a very dramatic growth of black holes. However, dual AGN in which the secondary AGN has comparable luminosity or is dominant are very rare. Only one known case was 49b, work by Seacrest et al. From 2018. So this is the image of WAS 49b, where you can see the B object is in the disk of the galaxy. It's a late stage merger. Next to it is X-ray image. So the secondary AGN is 200 times, I think, more luminous than the primary AGN, which is very unusual. And we found something similar. We named these 2 galaxies Swan and Odette. So we have a large galaxy and small tidal bridge, and a lot smaller galaxy at the end of the bridge, where secondary AGN residing in a smaller galaxy is slightly more luminous than the primary AGN. This is an early stage merger, second ever with comparable or dominant secondary AGN, but the first in an early stage merger, which can be very interesting for further studies of merger-driven accretion on the secondary AGN and growth of black holes. And finally, these are some images with different telescopes of the same system. And finally, I want to briefly talk about galaxy groups made completely out of dwarf galaxies. In 2017, Stewart et al. Found the first dwarf galaxy groups, 7 of them, containing each 3 to 5 members with separation of up to 100 kiloparsecs between the members. But there was no evidence for example, presence of intragroup gas in X-rays or the AGN in these systems. So we discovered something that's very interesting, redshift Z of 0.8, where we see the main galaxy. This is Hubble image, main galaxy in the center with mass in line with dwarf scenario, and at least 3 more nuclei around it. The red line is only 1 arc second, or around 10 kiloparsecs length. So all 4 nuclei are somewhere within 10 kiloparsecs of each other, and there's plenty of tidal features, tidal debris, tails from all nuclei. Further, I don't know if you can see anything because the contrast is really bad here, but this is James Webb image of the system. So this is the main nucleus. I hope you can see it. There is a secondary nucleus, tertiary, and the fourth nucleus. But if we change the contrast, we would see a long tidal tail here and tidal tail from this nucleus tracing whatever is seen in the HST image. We also find the evidence for the presence of AGN in the central galaxy of around 10 to the power 40 terabits per second, and a tentative discovery of an extended hot X-ray halo, which could imply that this is something between galaxy group and a fossil group, a collapsing group of old dwarfs, because the hot X-ray halo lives longer than the stellar component because it has longer relaxation times. And this would be the first direct evidence, direct example of hierarchical growth of objects, where we have multiple galaxies collapsing to create a larger one while having a bright AJ in the center. And that's all I have for you. Thank you.
Any questions?
Hi, thank you for your talk. I'm Jessie from Helsinki. Yeah, this is a really nice collection of observations, but I just wanted to know
to the difference in redshift. That is a clear evidence of the duality of the system. Then we could estimate the differences in the equivalent width or in the shapes. And we could also make a study in the of the intrinsic absorption lines that are of two types. The intrinsic one are at the redshift of the quasar, and so they can explain us which is the internal composition of the quasar. So if there are differences in these lines, we could say that the systems are different. While the intervening lines are a different redshift, not the one of the quasars, and so could give us some information about the host or the lens in the case of a lensed system. Here, there are the first example of dual systems, and in the first case, we see that there is a clear difference in the redshift, and as I just explained, there is also a difference in the narrow absorption line at the redshift of the quasar. The doublet of the magnesium-2 is clear in the violet spectrum, while is not shown in the light blue one. While here there is another example. I plot here the zoom of the magnesium line and the part of the spectrum in which there are a lot of narrow lines. And we see that there is a difference in the flux ratio. In fact, in the violet spectrum is clear the O2, while the neon 3 is bigger in the light blue spectrum. And so we can classify these two systems as dual. Here I show you a preliminary result of the first development that we made with this data. That is the measurement of the black hole masses, and we have the primary the measure of the black hole masses of the primary component in red, and in orange the mass of the secondary component, and we see that overplotted with the data obtained by Rakshit using the Sloan Digital Sky Survey data are well overlapped. But this is only a first result that we obtain, and we would like to enlarge these studies only on the data obtained with the KEK that I now show you. But first, let me show you an example of a lensed system. Here we see that applying a multiplicative factor of 13 to the light blue spectrum, we are able to well overplot the two spectrum here. And then we could also make further studies on the absorption lines. These are those at the redshift that is different from the quasar, and this is a redshift of 1.9. And so we could say that this could be the redshift of the lens, and so we could use it in order to make further follow-ups for the studies of the lens. Here I show you the first results that we obtained with STIS. This was the first GMP object observed with the results spectroscopy, and now we will have a lot of data, we hope, from HST because they accepted a new proposal. While here I show you the results in near infrared. In particular here we see the results obtained with KEK using the Osiris spectrograph, and we see only one line because it is a near infrared telescope, and we see that we can classify with the same method the system as dual and lensed. Here I show you a system that for us is not exciting because it is a superposition of an AGN and a star, but is the first object that we observed with Eris on VLT, and that was published by Manucci and it was the first article with Eris data. But we have a lot of time with the GTO, and so we had now some data that we should analyze, and so we hope to observe to classify several objects in the near future. So this is the plot that I show you at the beginning, and here we can see that below 7 kiloparsec, there are now a lot more systems than before, and the red circle are those one are detected with the GMP technique. So this technique is very useful to detect a system that have a separation lower than 7 kiloparsec, and we hope to find out other system in this part, and so we can use them in order to make further studies, such as the distribution of the black hole masses, but other things such as the estimate of the weight of the gravitational waves in the near futures, and so work in progress. And I leave you my summary of the studies. Thank you.
Welcome the next speaker, David Izquierdo Villalba from the University of Milano Bicocca.
So thank you, Ludovica. So yeah, I'm David Izquierdo. I'm a postdoc at the University of Milano Bicocca, working actually with Alberto Sessana, Monica Colpi, and collaborating with Silvia Bonoli, Daniele Spinoso, and Marta Volonteri. So today I'm going to speak about LISA massive black hole binaries, so massive black hole binaries below 10 to the 7 solar masses. So let me give a brief introduction. So I don't think I have to convince you or stress the fact that we know that massive black holes do reside in the center of the galaxies. Because, for instance, we have nice correlations between the mass of the central object, the massive black hole, but also the stellar mass of the galaxy, the velocity dispersion, whatever. But also we have luminosity functions, which are basically the manifestation, right, of massive black holes accreting matter in the center of the galaxy. But if we put everything in context, we have to take into account the fact that we are living in a hierarchical universe in which galaxies do actually merge very frequently, right? So if we put together these two pieces of evidence, we end up with the conclusion, right, that galaxies might host massive black hole binaries in the center of the galaxy. So even though, I mean, this is very nice to know, I mean, we know very little about massive black hole binaries because the wide dynamical range that we have to cover in order to understand from the formation than to the evolution and the final coalescence. No, I mean, as Christopher was saying this morning, I mean, we have a more or less nice picture about what is happening. So basically, after the galaxy-galaxy merger, the two massive black holes are deposited very far away, around kiloparsec scales, and thanks to the dynamical friction, the two massive black holes are able to sink to the center of the galaxy and eventually form a massive black hole binary, right? But dynamical friction is efficient only down to parsec scales. When we reach these parsec scales, we need further processes in order to, to shrink even further the binaries, right? And we need the interaction with circumbinary disk or the interaction with three single stars in the galactic bulge, and this is called hardening phase. Actually, when they reach subparsec scales, 10 to the minus 2, 10 to the minus 3, the emission of gravitational waves is the main driver of the massive black hole binary evolution, and they bring the two massive black holes to the final coalescence in very few mega years. I mean, actually, the emission of gravitational waves, I mean, can happen in different frequencies, and also the the loudness of the gravitational wave emission also depends in many different parameters of the massive black hole binary. The shear mass, which is a combination between the primary and secondary mass, the redshift, and also the binary separation. So if you want to populate this characteristic strength, which is the loudness of the gravitational waves and the frequency, we have different surveys that they are going to prove all this landscape, right? So we have current pulsar timing arrays, and we will have the future LISA interferometer. So actually, pulsar timing arrays are going to prove the existence of massive black hole binaries of 10 to the 7 solar masses, but in the relatively nearby universe, whereas LISA is going to be a complementary window, right, in which they are going to prove the existence of the lightest massive black holes, below 10 to the 7, but up to cosmological distances. So in this talk, as I told you, I mean, I'm going to focus on the LISA. And LISA is going to be extremely important because it's going to shed light on many different properties of massive black holes, from the formation, the growth, and so on, and the evolution between black holes and galaxies. But also, we know that massive black hole binaries in the center of the galaxies might be surrounded by, I mean, a lot of gas, right? So they can give also give rise to emission of electromagnetic counterparts. So actually, if you combine the detection of the gravitational wave together with the detection of the electromagnetic emission, you can constrain the luminosity distance and the redshift in a very different ways, right? So you can constrain even further, I mean, what is the distance redshift relationship, right? You can do cosmology with the multi-messenger astronomy. But even though this is very nice, I mean, it works in paper, it's actually very difficult because we have to detect the electromagnetic emission of the massive black hole binary. As this is not really easy, because the sky localization of LISA. So when LISA will fly and will detect a massive black hole binary and detect the gravitational waves, it's going to give you a patch of the sky in which the massive black hole binary should reside, right? But this sky localization can be extremely large. So this is an example in which there are 3 different binaries, just focusing this one, which is 10 to the 5. And this is the sky localization of the massive black hole binary. So you can see if we detect the binary up to months before the merger, the sky localization is very poor, up to thousands of square degrees. But if you detect the LISA massive black hole binaries at merger, actually the sky localization is way better and can be up to few square degrees. Despite this, it's not going to be easy. So let me show you why, because this is a virtual universe I did with a master student in Bicocca, in which we pick a virtual universe with massive black hole binaries, and we attach to this the sky localization of LISA. So with the red point is basically the massive black hole binary detected at merger, so the best case scenario, and the black points are the galaxies lying in this sky localization. So you can see just by eye that the number of galaxies placed in the LISA sky localization area is going to be extremely large. So it's going to be extremely difficult to determine which is the true host of the massive black hole binary and which one is the fake host. So it's going to hamper the possibility to do in multi-messenger astronomy. So yeah, it's going to be extremely difficult. So therefore, we need more theoretical studies in order to shed light on which galaxy we should pay attention and which galaxies we should just discard and don't even try to look for follow-ups, right? So for that reason, I'm going to address two different questions in this talk, which is what are the type of galaxies we should pay attention to when LISA massive black hole binaries are going to be detected, and if we can use any intrinsic or extrinsic property to basically unequivocally identify the LISA massive black hole binary host, and therefore do multi-messenger astronomy. So in order to answer these two questions, what I did is using a semi-analytical model, which is called El Galaxy semi-analytical model, which has a very complete model to track the formation and evolution of galaxies, because it includes many different recipes to track the star formation, whatever. Agent feedback, galaxy tidal disruption, so on and so forth, and is coupled with M-body simulations merger trees, so you can track from the very formation of the first halos down to the local universe. So in this talk, I'm going to use the Millennium 2 simulation, which is very high resolution and a fair enough volume. So actually, during the last year, on top of the galaxy formation model that includes the galaxy, we have coupled many different modules in order to track, for instance, the seeding model, how the first massive black holes form a high redshift, also the growth, but also the most important thing, including on the fly, the track and evolution of massive black hole binaries after galaxy-galaxy mergers. So what I did is pick in this semi-analytical model, build a virtual universe, and this is the example of one of those. This is the redshift versus the Rye ascension, and each point is a galaxy. So each galaxy can be whatever, a GN, a normal spiral galaxy, a dwarf galaxy, and depending on the merger history of this galaxy, each one can host or might not a massive black hole binary. So let me answer the first question, or let's address the first question. What are the typical hosts of the LISA massive black hole binaries? So what I did is picking all the galaxies, picking all the massive black hole binaries that are going to be in the LISA band. So for me, are going to be between 10 to the 4, 10 to the 7 massive black holes, binaries, below redshift 3, because I'm interested merely in the nearby universe. And then they are going to coalesce and below 1 megayear. So here I present you what is the typical stellar mass of the galaxies hosting these massive black hole binaries. So these different panels are different mass, beams of masses between 10 to the 4, 10 to the 5, 10 to the 5, 10 to the 6, and the bottom panel 10 to the 6, 10 to the 7. So you can see that regardless of the redshift, but also regardless of the mass, the host of the LISA massive black hole binaries are going to be dwarf galaxies, and they barely overpass 10 to the 9 solar masses. But what about the properties? So this is the specific star formation rate in the left and the gas fraction in the right as a function of redshift. So you can see that these dwarf galaxies are going to be star-forming galaxies, but are going to be also gas-rich galaxies. But now the question is, are these dwarf galaxies different from the rest of the dwarf galaxies? So we can use, for instance, the mass or the properties to disentangle between dwarf galaxies hosting LISA massive black hole binaries and dwarf galaxies that do not host LISA massive black hole binaries. So what I did is picking a control sample selected with the same mass in black hole of the LISA systems and overplot on top of this the properties. So you can see that, massive black hole, single massive black holes with the same mass of LISA systems are going to be placed in exactly the same type of galaxies. So the mass is not going to help to discard between true host and fake host. Regarding the properties, we find the same issue. Dwarf galaxies, hosting single massive black holes, display exactly the same specific star formation rate and gas fraction than binaries that are going to be seen by LISA. So basically, no, the mass is not a good discriminant to disentangle between true host and fake host, and the properties of the dwarf galaxies are going to be at all helpful in this search. So now the question is, can we use other properties in order to help or support this search? If you remember, I told you that massive black hole binaries are going to, they form thanks to mergers. So naively, you would think that merger features should be still present in the LISA massive black hole binary host. So what I did is, well, these are the typical properties. For instance, major features like streams, shells, or whatever, or tidal features, right? So what I did is, picking my Lisa massive black hole binaries, follow back the merger tree of these galaxies, and compute what is this delta TV, which is the time elapsed between the galaxy merger and actually detection of the massive black hole binary. So if this time is smaller than certain threshold I put 2 giga-year, the galaxy didn't have time to relax, and the merger features should still present in the galaxy. If it's larger, that the galaxy had time to relax, and we will see a normal dwarf galaxy. So what the results maybe are a little bit overcrowded, but I mean, let me summarize everything in these 2 lines. So the 90% of high-resolution hosts of Lisa massive black hole binaries will display visible merger features. On the other hand, when you go down to redshift, for instance, redshift 1, only 10% of the Lisa hosts will display these merger features. So, okay, I mean, Lisa massive black hole binaries are hosts are going to display merger feature, especially high redshift. But the question is again, dwarf galaxies without any massive black hole binary are going to display exactly the same merger feature. So can we use these merger features such like a smoke gun for detecting the Lisa massive black hole binary host? So I don't want to show you anything quantitative or qualitative. So this is the sky localization of Lisa of a massive black hole binary of 10 to the 5 solar masses, and in here 10 to the 6. And each point is basically a dwarf galaxy placed in this Lisa sky localization area. So the star is the true host, where the Lisa massive black hole binary is, and the point are basically dwarf galaxies which might or not display merger features. So in blue and red are dwarf galaxies which actually do display the same merger feature than Lisa host, and in black are the dwarf galaxies without any merger feature. So you can see just by eye that the plot is very colorful, right? So it's not really a good point. I mean, Lisa massive black hole binaries are going to be placed in dwarf galaxies, which are going to be crowded of dwarf galaxies exactly with the same mass, of course, the same star formation rate, gas fraction, but also the same merger features. So basically, dwarf galaxies, I mean, the merger features are going to be really useful in the detection of the Lisa massive black hole binary host. And this is more quantitative. This is just the previous plot, but quantified, which is 50% of probability of finding at least one dwarf galaxy in the Lisa sky localization with the same properties and merger features. So these are my conclusions. So I just try to give a message. I mean, if you want to do cosmology with Lisa massive black hole binaries, you must be very careful, because you must find the true host. And if you don't rely, for instance, in any AGN emission, and you only look for galaxies, massive black hole binaries of Lisa are going to be placed in dwarf galaxies with the properties that are not at all different from normal dwarf galaxies. On top of this, the merger features are going to be also very similar to normal merger features that are going to display dwarf galaxies in the patch of the sky that you are going to put and to target the search of the Lisa massive black hole binary. And that's everything. Thanks for the attention.
Okay, so please welcome the next and the last speaker of this session, Chin Andong Paetz, is it right? Okay, from the Institute d'Astrophysique de Paris.
Hello. Yeah, so my name is Andong Paetz. I'm a PhD student in IAP in Paris. I'm working with Marta Volonteri, Joan Dubois. Today I will be presenting a project which is entitled Multi-Messenger Modeling of Massive Black Hole Mergers in the Obelisk Cosmological Simulation. So yeah, this is based on a series of papers that we published earlier in the year. So yeah, luckily all the people already did very nice introductions, especially David on this, so luckily I can go a little bit faster here. So yeah, the general picture for massive black hole mergers is that of course you have black holes in the center of most galaxies, so therefore as galaxies merge, you will expect that if the evolution of the interaction is fast enough and the black holes sink due to dynamical friction fast enough, then the two black holes can form a binary, the black holes from each of the galaxy. And then if the binary evolution timescale is short enough, you will have a massive black hole merger eventually. So these massive black hole mergers emit both gravitational waves and are also expected to emit electromagnetic radiation. And combining the two of them, we can obtain complementary information about the merger, so the physics of the merger, the environment of the merger, and also the astrophysical population of black holes and galaxies producing these mergers. So we want to study this from a theoretical perspective to characterize the population and the detectability of black hole mergers. So our starting point is a cosmological simulation, which is the Obelisk simulation. So we take the black hole population from here. And this simulation is a zoom-in simulation that follows the evolution of a protocluster down to a redshift of 3.5. So therefore, since we're following an overdensity, we have more mergers than average. This simulation includes many of the usual prescriptions for cooling, star formation, supernovae, the creation of metals, etc. But most importantly, we have many subgrid models for black hole physics. These include black hole seeding at high redshift using a density criterion. We also include, as usual, models for accretion, for feedback, so the release of energy to the environment. We also have a model for spin evolution, so spin is computed on the fly, but also impacts the simulation. So that is, for example, the radiative efficiency of the black hole is determined according to the spin, and so the spin is updated by gas accretion and merges with other black holes. And we also have subgrid models for the dynamics, for the unresolved dynamical friction from gas and stars and collisionless particles. And finally, we have high resolution. So with all this in mind, we expect to have a realistic population of black holes that are hopefully representative of the real thing. So with this in mind, we aim to answer a few questions. So the first question, which is more related to the David talk, I'll go a little bit more quickly on this, but I'm happy to discuss more results later if you're interested. Which is, how does the merging black hole population compare to the global black hole population? So in other words, if we manage to find out about the merging black hole population, what inferences can we make about the global population of black holes? And so here I'm showing the distribution, so in blue for black hole mergers, so for the mass of the host galaxy here in the left, and the total mass of the binary on the right, and then for the global population of black holes in galaxies in orange. And the first thing you can notice is that the massive black hole merger hosts tend to be more massive for in the case of mergers than for the overall population of non-merging black holes. And the main effect driving this is the occupation fraction of massive black holes. So less massive galaxies do not tend to have a black hole in the center. And then since, well, due to the well-known correlation between galaxy mass, host galaxy mass, and black hole mass, this leads also to a higher distribution in black hole mass for mergers compared to the global population of black holes. Okay, so moving on to the second question. Now, given that we have characterized a little bit the population of massive black holes, we can ask the question of whether these massive black hole mergers can be detected with current or future instruments. And if so, we can, since we are using a simulation, we can characterize the bias, the observational bias. But first, so the simulation doesn't include the direct observational properties, so we have to include them in post-processing from the information that we do have in the simulation. So the first thing we might do is to calculate the gravitational wave emission and simulate the parameter estimation and detection by LISA. Then we can also model the electromagnetic emission in different bands using an LCD model and also in the radio. So for the radio, given the theoretical uncertainty, we include two models. One is a more theoretical model based on the Bland-Fossenac effect, and the second one is a more phenomenological one based on the fundamental plane of black hole accretion. And yeah, importantly, I don't know if I have time to cover this, but in order to hopefully characterize the merger observationally as such, we model the presence of a transient, so an increase or decrease, so a change in flux, essentially, that could help label the event as a merger indeed. So we include two possible models. One is some increase in the Eddington ratio due to the merger, so increasing the accretion rate, driving it to the maximum Eddington rate. And then some radio flare, so radio flare due to the increasing point in flux. And finally, we have to model some non-ideal effects. In particular, so we need to model the obscuration due to gas and dust intervening between the galaxy and the observer. And also we need to model the contaminant, well, in our case it's contaminant emission due to the galaxy, because the galaxy will be emitting as well. And so if the emission due to the galaxy is too large, it will be more difficult to detect the black hole merger. And so, well, let's start from with the gravitational waves. In this plot, I'm showing in the top panel distribution in signal-to-noise ratio with LISA, for detection with LISA, for our merger sample. And here we set a detectability threshold at 10, a signal-to-noise ratio of 10. We find that most of our merger, in fact 99% of them, can be detected with LISA, and generally with very high signal-to-noise ratio. And well, there's a small population of very high mass mergers with unequal mass ratios that are not detected, but this is generally subdominant. And also, the parameters are equally well constrained by LISA, such as the redshift, masses, and spins. But if you look at the bottom panel, in the bottom panel I'm showing the error in the sky localization, so that is how well can LISA constrain the position in the sky of the source, and generally the systems are not well localized. So if you have a look at the plot, almost 2/3 of the mergers have a 2 sigma error, yeah, larger than 10 square degrees. This is larger than the field of view of most telescopes. So if we want to do electromagnetic follow-up, then we will need probably to tile the sky or to use different telescopes, different instruments to cover the error, the error region. So now we can move to the electromagnetic side of things. So here in this plot, I'm showing the black hole flux in the y-axis and the host galaxy flux in the x-axis. So this horizontal diagonal line denotes the equality. So ideally, we want to be above this line so that the light from the merger exceeds the light from the galaxy, and it's easier to observe. And then we also set some detectability, some reasonable detectability limits based on the sensitivity of current and future instruments. Okay, so in the left panel, I'm showing the picture in the UV, and in the UV, the main conclusion is that most of the merger are very heavily so the light is very heavily dominated by light of the host galaxy. So then it's relatively difficult. Well, it will be quite difficult to disentangle the emission from the black hole. So then, in our case, the UV, we find that the UV is not the best avenue in this sense. Whereas in the X-ray, the situation is much better. So here we're showing the total X-ray interradiating flux in this band, and then in this case you do get some fraction of mergers that are both above the sensitivity threshold and that dominate the light of the galaxy, and these are around 5%. And also, if we consider some rebrightening event, as I said, that increases the accretion rate to Eddington, then this fraction becomes larger. And so another thing we can look at is the transients. So if we consider that the source initially has some accretion rate, and then at the merger the accretion rate increases to the Eddington limit, we can look at this difference and see if it's large enough to be significant. So here we set some kind of arbitrary limits for observability. We say that this transient can be observed if either the source is observable both before and after the merger, and the change in flux is larger than a factor of 2. We say that we can also observe the mergers if we You also say that we can observe the transient if the source is unobserved and then observed after the merger, or in the converse case, if it's observed and then unobserved. And in this case, you see that there's some fraction of merger that fulfill one of these conditions. Okay, perfect. So going back to this plot here. So we found here a population of black hole mergers that in principle can be observed. So we may ask the question, how is this population of mergers biased with respect to the global population of black hole mergers? And well, this is shown here in this plot. Here I'm showing the distribution of some parameters, such as the host galaxy mass, the redshift of the source, the total black hole mass, and the Eddington ratio, that is the accretion rate, and comparing the observable mergers in yellow and the global population of mergers in blue. And the main conclusion from this plot is that so naturally, since more massive black holes and more highly accreting black holes are more luminous, then they will be more likely to be observed. And there's a bias for high masses, high accretion rates, and also since you get higher masses, so black hole had more time to grow at later times, then you also have a bias for lower redshifts. Finally, another bias we can look at is here in the correlation between black hole mass and galaxy mass. So if you compare the two curves, you see that at these kind of intermediate masses, there is a bias in black hole mass at fixed galaxy mass. So if we try to infer this correlation, we might be a little bit biased just using the detected mergers. Okay, finally, I'm gonna finish here, I think. I'll go very briefly through this. We can do the same thing that we did in the X-rays for the radio. So here I'm showing the black hole mass as a function of the spectral flux in the radio, and a frequency of 2 gigahertz, and then the sensitivity limits for a 5 sigma detection in several future observatories. And then again, well, these for both of our models, and again, some fraction of them can be detected in the radio, and this depends a lot on the theoretical uncertainties are on the instruments that we use. And yeah, of course, for our pessimistic model, which in our case is like the empirically based model, only very massive black holes can be detected. So this is a similar conclusion that as in the X-rays. Yeah. Do you have time for? Okay, perfect. So yeah, this is actually the last slide. So finally, we made combine both the information from the gravitational waves and from the electromagnetic emission. And so if you look here, so I'm showing the signal-to-noise ratio from LISA for all the mergers, and then for radio observable and X-ray observable mergers. And here the good news is that electromagnetically observed mergers can also be observed in the gravitational waves. But for the scalar localization, the prospect is a bit worse, since the scalar localization tends to get poorer for electromagnetically detected mergers. So yeah, that's it. Thanks a lot, and I'm happy to take any questions.
So questions?
Okay, so welcome everyone to the post-games afternoon session. Our first speaker is Ludovica Varisco from Milano Bicocca. So take it away, thank you.
Thank you. Hi everyone, it's me again. My name is Ludovica Varisco, and I'm a PhD student at the University of Milano Bicocca, and I'm working with Elisa, Matteo, Massimo, and Alessandro Lupi. And today I will talk to you about this work in which we are trying to build an effective model for the tidal disruption of satellites in minor mergers. So I will start with a bit of context. So from the Lambda-CDM model of cosmology, we know that the formation of cosmic structure proceeds through a series of repeated mergers, and many of them are actually minor merger. And when we are in a minor merger scenario, we have a satellite galaxy which is moving within a larger galaxy. And during its orbital motion, it will sink toward the center of the host due to dynamical friction while losing part of its mass. And if both of the merging systems contain a massive black hole at their center, if the dynamical friction is efficient enough in bringing the satellite toward the center of the host, it is possible that the two black holes will form a bound binary, which can eventually lead the final coalescence with the emission of gravitational waves, which will be detectable, for instance, by LISA. And actually, at the present time, we are in a very favorable moment to study those kind of systems. In fact, with the future coming of the LISA mission, which will probe the massive black hole binary merger and the hierarchical aggregation of cosmic structures, and the present Gaia mission, which is tracking the orbit of stars and stellar cluster in our Milky Way, is giving invaluable information on the evolution and on the merging history of our galaxy. However, from a theoretical point of view, studying the merger of galaxies still remain very challenging. On one end, we have n-body simulation, which are typically very computationally expensive and can be very limited both in spatial and mass resolution. Sorry. And on the other end, we have semi-analytical models, which typically accounts only for very simple systems and hardly account for stochastic effects. That's why my work is actually part of a collective work in which we are trying to build a semi-analytical computational framework that could encode the most realistic as possible dynamics of massive perturber in multi-component galaxies. And this implementation includes a detailed prescription for dynamical friction adapted for both flat and rotating systems, the interaction of the massive perturber with structures such as spirals and bars, and what I'm working on now is to also include the mass evolution of an extended satellite due to the tidal effects from host galaxy of different geometries. So, as I mentioned to you before, when we are in a minor merger scenario, we have a satellite galaxy which is moving within a larger and more massive galaxy, and during its orbital motion, it will be subjected to tidal forces that will act by stripping part of its mass from beyond a certain limiting radius, which is often called the tidal radius. And I would say that a detailed prescription for the mass evolution of the satellite is crucial, since the mass loss caused by the tidal forces can significantly impact the efficiency at which dynamical friction can bring the satellite toward the center of the system. However, all the prescriptions present in literature for the tidal radius are made under the simplistic assumption of a spherically symmetric host. But we know that galaxy can include very highly non-spherical components, such as disks, and that's why the main aim of this work is to propose a new model for the tidal stripping-driven mass evolution of an extended satellite in a host galaxy of any geometry. Okay, so now if we want to define the tidal radius, let us first of all consider once again a minor merger. And at this point, let's put ourselves in the reference frame of the satellite and consider a test particle in it. At this point, we can compute the acceleration of this test particle along the radial direction from the center of the satellite, which is the one that I'm showing you up here. And at this point, the tidal radius is simply defined at the distance from the center of the satellite at which this acceleration equals 0. So if we first make 3 simple assumptions, so the first is that the host is spherically symmetric. If we then consider that the test particle distance from the center of the satellite should be much lower than its distance from the center of the host. And finally, if we consider the test star to be on the direction connected the center of the 2 systems, what we find is that the solution of this equation is simply the definition of the tidal radius proposed by King in 1962, which is the most commonly used. In our case, however, we want to consider a generic galactic field. So what we did was to relax all of these assumptions. And basically what we did was to consider many different directions from the center of the host. And for each direction, we numerically solved this equation to find an estimate of the tidal radius. And then we pick as a definition of the tidal radius the minimum of the tidal radii computed along all the different directions. Okay, at this point, since we want to account for the fact that the mass loss actually is not instantaneous, especially for a very eccentric orbit, what we did was to introduce also a second definition for the tidal radius, which is based on the tidal radius computed at the previous time with an exponential decrease where the time scale is the orbital time of the satellite about the galaxy, and alpha is a free parameter of the order of the unity which we tune on the simulations. Finally, we consider the tidal radius at any time to be the minimum of the 2. And lastly, we consider an additional condition in which we ask the tidal radius to be a decreasing function of time, which basically means that we are considering the tidal stripping, so the mass loss, to be unreversible. So once that I lost a portion of the mass, it will remain unbound forever. Okay, at this point, we simply consider, for the mass evolution of the satellite, we simply consider at any time the mass of the satellite to be the initial theoretical profile truncated at its tidal radius. So now that we have our semi-analytical model, we validated our model against n-body simulations. And now I will show the result that we obtained from some of these, the model that we tested. And as a first set of simulations, we consider cases in which we do not account for dynamical friction. This is simply because the simulation were way faster and the model was easy to test. And in this specific case, I'm showing you a case in which we have a spherically symmetric satellite, which is composed of 10 to the 5 particles and follows an Arquist profile. And then the host galaxy is a disk, exponential disk, and it's included in the n-body simulation as an analytical potential. In this specific case here, I'm showing you the results for a satellite which is moving within the galactic plane. And on the left panel, we have the three-dimensional trajectory of the center of the satellite in black from the embodied simulation, and with the orange dashed line are the prediction of our semi-analytical model. While on the right-hand panel, we have the time evolution of the relative error between mass computing estimated by our semi-analytical model and the mass in the embodied simulations. So basically, if we are in the positive region of this plot, we are overestimating the mass of the satellite, while if we are in the negative region, we are underestimating the mass of the satellite. The solid line here refers to the result that we obtain using our prescription, while the dashed line is a comparison with the King model. And in this case, we can see that our model better describes and better reproduces the results of embodied simulations. We also consider different inclination of the orbit of the satellite. In this case, the satellite is the same as before, and also the initial velocity. And we have an orbit which is inclined of an angle of 30 degrees, no, 60 degrees, and 90 degrees, and we can see that in all of these cases we have a good agreement with embodied simulation, both in the orbital and in the mass evolution. We also tested different scale radii of the satellites at different initial velocities, and these three plots are the same for. From the left to the right, with decreasing initial velocity with respect to the circular velocities, 75, 50, and 25, while the different color refers to different scale radii of the satellite, and once again, solid line refers to our results, while the dashed line is a comparison with the King model. And for all of these models, we can see that once again, our model better describes and better reproduces the embodied simulations. Okay, finally, we are also considering multi-component galaxies, and in this case, the satellite is exactly the same as before. The host galaxy instead is composed by a disk, which this time is no more analytical, but is composed by 10 to the 7 particles, and a halo, which instead is analytical. So in this case, we do have the dynamical friction, but the only contribution to dynamical friction is given by a disk. In the plot on the left, I will show once again the trajectory of the center of the satellite, but this time I also show you the particles of the satellite, and as you prefer. Okay, so in yellow here we have the particles that are bound to the satellite, while in gray those that has been stripped, while the two solid lines will track the evolution of the center of the satellite in red from our semi-analytical model and in black from the embodied simulation. Sorry. Okay, once again, on the right we have the relative error on the mass as the evolution of the error on the estimate of the masses, and once again we see that our model better reproduces and matches the embodied simulations. So to conclude, we propose a new prescription for the tidal radius and the mass evolution in minor merger, which is suitable for different host geometries. we find that our model is in general in good agreement with the embodied simulation for all of the different geometries that we tested. And also we found for all of the models a higher accuracy in reproduce embodied simulation with respect of the cases in which we use the King prescription. So this is all, and I thank you for your attention.
Okay. Well, thank you first of all to the organising committee for allowing me to speak today. It's a great pleasure. So I'm Nader Konji. I'm a third-year Ph.D. student at University of Surrey, and I'm going to be talking to you about comparing large core formation by binary scouring and gravitational wave recoil in massive elliptical galaxies. So if we look at a typical giant elliptical galaxy, they don't look very exciting. This is a typical picture on the bottom right. But actually, I'd like to say they are quite interesting objects. First of all, they're very massive. They're the most massive galaxies in the universe. And so they're the end point of the hierarchical merger paradigm from lambda CDM cosmology. And also, interestingly, a study showed that they are the most likely galaxies to have life. So, yeah, quite interesting objects. Now, when King looked at these galaxies back in 1978, he noticed that there was a flattening of the central part of the light profile. And this became known as a core. Following this, larger surveys indicated that there was a tendency for the more massive elliptical galaxies to have this flattening, have a core, but the smaller elliptical galaxies would continue upwards towards the center as a cusp. And I've shown two light profiles here from Lauer's study in 1995, which shows the two types from HST data that they analyzed. So the immediate question that arises is, how do these cores form? Well, we believe that each galaxy contains a supermassive black hole. And so evidence from simulations shows that cores can be formed during major mergers. So I'm sure a lot of you know these three phases that occur, at least in simulations, during a major merger. So we get dynamical friction, first of all, where the supermassive black holes have a drag force exerted on them and they sink towards the center. Then secondly, binary scouring, which is a rapid hardening of the formed supermassive black hole binary. And during this process, you get many three-body interactions with the neighboring stars and their gravitational slingshot ejection. And so this is the most accepted method for formation of a core. But we also know that if the black holes get close enough together, gravitational wave emission becomes important. And with that, we can lead to a further inspiral of the black holes until they can coalesce. Now, when they coalesce, depending on the orientation of their spins, they can get a gravitational wave recoil kick. And if this is maximal, this can be of the order of 5,000 kilometers a second, and so can even eject the black hole from the galaxy completely. So that the recoil kick is obviously another mechanism which could potentially form a core. So the aim of this study is to compare core formation by binary scouring and gravitational wave recoil. And we want to look at predominantly the size and flatness of the cores, but also we want to try and see if we can find out anything about energy and angular momentum transfer. So what we did was major merger simulations. These were one-to-one mergers, and they were based on observed properties of known galaxies that have large cores, taken from Darlow's paper in 2019. After the binary hardens, the black holes are then merged and given a gravitational wave kick. And just to mention, today I'll only be presenting results from 2 of the 4 galaxies in terms of the kicks, because they're still running at the moment. So these are the 4 galaxies we chose, and really what we wanted was a nice variation in the core size. So we're going from about half a kiloparsec core size to almost 3. And these have a variety of Cirsic indices, effective radii, and black hole masses ranging from 1.7 to 6.45 times 10 to the 10 solar masses. So just a bit more detail on how we set things up. So we used the Agama action-based software by Eugene Vasiliev to create a combined potential with a black hole, a Cirsic modeled stellar bulge, and an NFW dark matter halo. Then Agama then samples using a spherical distribution function to give us the bulge and halo particle positions and velocities. For the initial merger, we use a resolution of 1 million particles per galaxy, and we set them off in a Kepler orbit with high eccentricity because we wanted to match the high eccentricity seen in cosmological simulations of major mergers. And we started at a apocenter distance of 80 kiloparsecs. For the actual n-body code, we used the Griffin code, which is the fast multiple method by Walter Denon. So this is just to show the initial phase of the merger. This is the black hole separation over time for the 4 different galaxies, and just showing that with the different galaxy characteristics, the merger does proceed slightly differently in each case. And this is an animation of a gravitational wave kick. So this is a 0.9 off escape velocity gravitational wave kick, so very big kick. And basically the black hole in orange there is passing through multiple times, getting out to about 300 kiloparsecs initially, and gradually the motion's damped down. It makes around 100 passages before it slows down to Brownian motion at the center. And this takes a long time, so this is well over a Hubble time for it to settle down. And this is again to emphasize the massive difference between a 0.3 of escape velocity kick and a 0.9. So in a 0.3 escape velocity kick, the black hole only gets a few kiloparsecs out, and it's all over in about 50 megayears. Whereas for the 0.9 kick, as I say, it's going to over 300 kiloparsecs, multiple passages, and taking over a Hubble time to settle down. So on to the main results, which is looking at the core formation. Here are the density profiles for all 4 galaxies. Oh, sorry, this is the first 2 actually. First 2 galaxies, 3D density on the left, surface density on the right. And as you can see that after binary scouring, a core is formed in each case, but they're not particularly flat. They're all a little bit cuspy, especially in 3D. But now if we add on, the remaining 2 galaxies first. And the thing to mention here is that 8261 is flatter, and that's because it starts off with a very low Cirsic index. But if we add in the effect of recoil, so this is recoil as the black holes just reach the first apocenter. And it's quite dramatic, I think, that straight away, in all cases of the kicks, the profile is straight away flattened, much more flat, which I think is a very interesting result. And the other thing to note is that the core doesn't really seem to get any bigger by this stage. So much flatter, but not bigger. And also, no difference at all between the different size of kicks at this point. So that initial burst doesn't seem to make any difference initially. But if we move to the end of the gravitational wave recall kick, we will see a dramatic difference. So now the 0.3 doesn't really change anymore, but as we go up in gravitational wave kick, we get more and more massive cores in both cases, but particularly in the case of NGC 1600. But how long does it take to form these massive cores? Actually a long time. So in the case of NGC 1600, this is the 0.9 off escape velocity kick, we can see that first few passages it's making a lot of difference. Even up to the 50th passage, there's still a lot of core enlargement happening, which is taking about a Hubble time. And even between the 50th and 100th passage, the core is still enlarging. So to make this a bit more quantitative, I've done some core Cercic fitting. So this is a 6-parameter profile. And the two important parameters for core fitting are RB, the break radius, which equates to the core size, and gamma, the inner logarithmic slope, which is showing how flat the core is. So just a couple of example fits. So this was NGC 1600 at the end of scouring. So we can see the data in blue and the fitted profile in orange. And it seems a pretty good fit, especially around the core region that we're interested in. This is an example fit after recoil. Now, I chose this one because the core Cercic profile can be a bit degenerate because there's so many parameters. So for this one, you can get a very good fit, but end up with an unphysical result. So I was initially getting a very low effective radius, about 1 kiloparsec. But what I found was that if I set an upper limit to the Cercic index, I could then still get a nice fit, but also a more physical overall profile. So this is all the fits that I've done so far. As I say, it's still ongoing. But we've got the results for after scouring. And it's very striking that for NGC 1600, we've almost completely matched the observed core size after scouring. And this is with very wide parameters on the fit, so nothing particularly done there at all to achieve that. That was just straight out of the box. A2147, we got slightly bigger size than the observed size after scouring. So we could say for these two galaxies, it looks like binary scouring is sufficient to create the observed core. But for the remaining two galaxies, we did not manage to get a big enough core to match the observations just with scouring alone. And the other thing to point out is that the gammas show that the profiles are all still quite cuspy. Looking at the kicks, we see some really nice progression in core size with increasing gravitational wave kicks. And we can also see that the cores are much flatter. One interesting point here is that for A2261, we got almost exactly the observed core size with a 0.5 gravitational wave kick. So this seems to indicate that you need more than a 0.3 kick to achieve that observed size. So just a little bit on orbital analysis. This is just to show that initially there's no predisposition in our orbits with the initial conditions, but at the merger and even more so after the kick, we get a circular predisposition in the inner part of the galaxy and increase in radial orbits in the outer part. And please regard this as experimental. This is the latest thing I'm doing, which is trying to do EJ maps for during the merger process. So I don't want to comment too much on this at the moment, but just to say that in the initial merger, we're getting a mixing and a very big spreading out of energies. And then with the gravitational wave kicks, we're getting progressive loss of the low angular momentum particles with increasing kick, which is very noticeable on the gravitational wave 0.9. Okay, so that's all I really wanted to say. I'll leave it with the conclusions and happy to take questions. Thank you for your attention.
Okay, thank you very much, Nader. Okay, so I see questions. From,
yes.
From the University of Helsinki. So, take it
Yeah. So, hi everyone. It's now time for another Ketju talk. So, I'm Atte Keittaranta. I'm a second-year Ph.D. student from University of Helsinki, working in the same group as Jessica and Dimitrios are. And the title of my talk is Capturing Dynamical Friction, Supermassive Black Hole Dynamics with Ketju and Subgrid Models. So, this has been talked quite a few times already today, but the dynamical friction is the first phase of binary evolution. So, as there's forms an overdense wake behind the black hole, it starts to fall into the center from kiloparsec scales. And then after that, complex three-body interactions and gas physics drive the binary into sub-parsec scale separations, and then gravitational wave emission makes the binary to merge. And the plot I show here is from a simulation I will discuss more in a bit. So Ketju has already been talked quite a few times here, but simply put, Ketju removes softening for supermassive black holes using a regularized integrator, and this integrator is used for stellar particles that are near the black hole within 3 softening lengths from it. And outside this region, standard gadget stuff is used. And for supermassive black hole binaries, the post-Newtonian correction terms are included up to the term 3.5. And the simulations I will show here are done with gadget 3, but there's also gadget 4 version, which is publicly available. So if you're interested, you can take a look. And the Ketju talks so far have all dealt with simulations where the resolutions are really high, but I'm here focusing on simulations where it's really low, so cosmological simulations. And in cosmological simulations, the seed masses are usually quite low, of the order or even smaller than the masses of the surrounding particles, so repositioning is often used, which means that the black holes are in each time step fixed to be at the minimum of the local potential. And also in recent simulations, subgrid models are often used instead of repositioning, meaning that additional acceleration terms are added for black holes in order to take unresolved effects into account. And what has been previously done in our group is to also use Ketju in cosmological simulations, but this has only been possible for quite low redshifts of smaller than 0.8. And this is because Ketju requires quite a large mass ratio between the black hole and stellar particles, meaning that it doesn't really work for seed masses. So in these simulations, repositioning is first used to run the whole thing, and then from that, a snapshot is picked by hand, and from that, the simulation is run again with Ketju. And then shortly about these dynamical friction models. So one model that has been already used in cosmological simulations is the Tremel-L'Étal model, which is based on the Sand-Shekhar dynamical friction formula. And this has been used in the Romulus simulation, and it predicts quite a large number of wandering black holes in the galaxies. And in this you sort of integrate over the nearby field particles. And another new alternative to this is from this year, Ma et al. Discrete dynamical friction model, where you, instead of integrating over the field particles, you sum over all the field particles. So what we wanted to take a closer look into is how does these subgrid models compare to Ketju, and how does this work in different resolutions. And also we now want to move away from repositioning in our cosmological simulations. So we would no longer need to pick the Ketju integration starts by hand, and now we could also take a closer look into higher redshift systems. So the first simulations we did was very simple black hole sinking in a Plummer sphere. And the black hole is first set into a circular orbit. And the good thing here is that analytic solution or estimate is known for the black hole. And the black hole mass here is 10 to the power 7, and this is done with 2 different black hole stellar particle mass ratios, 10 and 100. And these simulations are done with Ketju, with these 2 subgrid models I mentioned, and with standard gadget tree. And for each, there's 5 different runs, all different realizations of the same density profile. And these plots here show the difference between the simulations and the analytical estimate. So here, GetU actually does quite well, even in the smaller resolution. It stays roughly within half a kiloparsec from the analytic estimate, and the Tremel model does equally as well. But interestingly, the Ma et al. Model here, with the higher resolution, actually sort of double counts gravity here, so the correction terms are a bit too large. And also the gadget simulations here and here doesn't really sync the black holes to the centers. So how about mergers then, galaxy mergers? So next thing we did was unequal mass galaxy mergers, where the higher mass black hole has 10 to the power of 8 solar masses, and the lower is 10 to the power of 7. And also now the GetU merger criteria is that the black holes merge if they are within 12 short-field radii from each other, and for the other ones, the black holes merge if they are within a softering length, and this relation or criteria is fulfilled. And these are now done with 3 different resolutions or mass ratios, 100, 1000, and 10,000 for the larger black hole. So for the smaller one, they are 10, 100, and 1000. And unfortunately, these are not yet done for the discrete dynamical friction model. So this quite busy plot here shows the separation between the 2 black holes, and the vertical lines show the points or times of mergers. So with the highest resolution, the Tremel model always merges roughly at 5 gigayears, and at the same time, the GetU runs start to get into parsec scale separations. But here the GetU runs do not merge at all. So the black holes, the binaries here stay at eccentric parsec scale orbits. And as we move into smaller worse resolutions, the Tremel still always merges, but it's now more scattered, and GetU still falls into parsec scale orbits, but it's also now getting more scattered. And as we go into an even worse resolution, GetU doesn't anymore really work, and the Tremel model still merges, but now the mergers happen roughly half a gigayear earlier than before. And now, as I mentioned before, we now want to model all the 3 phases in cosmological setting with GetU on from the beginning. So what we decided to do is to combine GetU with this Tremel subgrid model. So there's a mass limit for GetU integration, and if a black hole is above this limit, GetU integration is used. If it's below it, and also the black hole is outside another black hole's GetU region, the Tremel subgrid model is used. And we now tested this in a cosmological zoom-in simulation, where the GetU mass limit is 10 to the power 7.5. The black hole seed mass is quite large, 10 to the power 6, and the baryon mass is 2 times 10 to the power 5. And the following figures are really preliminary. So first, this simulation is now at redshift 2.39, and there are currently 6 black holes that are above the GetU mass limit. And the virial masses of these systems where the GetU black holes are within 2 times 10 to the power of 11 and 10 to the power of 12 solar masses. And currently, there's one GetU integrated binary system, which is shown here. So first, there's dark matter surface density, and then baryon surface density for one of the galaxies, and then there's at the center there's 2 black holes that are now less than a parsec away from each other. And there has been one GetU integrated merger so far in this simulation, which occurred at redshift 2.73. And at the moment of mergers, the masses of the 2 black holes were 6 times 10 to the power of 7 and 4 times 10 to the power of 7. And the binary parameters are shown here. So this is the semi-major axis, and this is the eccentricity. So the binary had a relatively high eccentricity of around 0.8. And if we didn't use the Getty integration, but rather just the subgrid model and the standard merger criteria, this vertical line shows the moment of merger. So using Getty here delays the merger by roughly 50 megayears. And then I took a quick look into comparing this merger with LISA sensitivity. So this is done with the Phenom-D software. And here the characteristic strain is for a moment in the LISA sensitivity band. And here the Getty and the subgrid modeled mergers are roughly the same because they happen still roughly at the same redshift, and during this 50 megayear delay, the black holes do not grow by a noticeable amount. And then also I took a quick look into wanderers around these Getty systems. So here a wanderer just simply means that it's a non-Getty black hole that is within a virial radius of a system with a Getty black hole. And almost all wanderers here are seed mass black holes. There's one larger black hole, but that's actually another galaxy within the virial radius falling into the system. And on average, these systems have 5 wanderers per system. So to conclude, in terms of dynamical friction, the Getty and the Dremel subgrid models actually agree quite well, especially if the resolution isn't really low. And now that we have combined Getty with the dynamical subgrid model, we can now run Getty from the start of a cosmological simulation, which means that we can now start to take closer looks into higher redshift systems with Getty. So that's all. Thank you for your attention.
discussion session about the massive black hole pairs and binaries. So, questions? So let's start with basics ones. So this morning, at some point we discussed about what is a galaxy merger. So maybe we can start from this, since this concept seems not obvious to everyone. So any comments about how defining a merger from observational point of view and also from the simulation point of view, of course? Tommaso, would you want to start?
Yes, I want to say something about the simulation point of view. Okay, so I don't know, to my knowledge, I don't know how many, but am I supposed to use this?
Yes.
Is necessary?
Yes.
Okay, sorry. So, to my knowledge, I don't think there is a clear criterion to define a merger from the simulation perspective. Correct me if I'm wrong. Because I don't know it. I mean, if you know, maybe you know. So nobody's saying anything. So there is nothing like. Okay. Elisa knows about it.
I don't know anything, but I mean, I know there are tools like halo finders, for instance, in cosmological simulations, and you can kind of see when a smaller halo enters a bigger halo or stuff like that. And this could be a way to define a merger and the way in which you build merger trees typically. So this could be a possibility.
Yes, this is true, and but at that point we would just move the criterion, because at a certain point you would stop defining and identifying every single structure. At a certain point, when you have two galaxies merging, they would stop being two separate objects, and they would be just one. So my question at that point would be when, and so that would be the criterion. Again, when you see two galaxies, then to go just to the observation perspective, when you would say, okay, those galaxies are clearly interacting, but we are still speaking about two galaxies, and when it is just a galaxy which is very messy, because maybe it is just slightly post-merge. I have some ideas, but I wanted to know what do you think about it.
So just very quick, I'm a little bit ignorant in the field, so perhaps my idea can be wrong. So every galaxy has a virial radius. If the two galaxies are within a factor of 2 or 3 or 5 of the virial radius, they will likely end up one in the other, right? So perhaps even a factor of 10. If you think our galaxy and Andromeda, someone can consider what's happening in our local group, which is a good comparison because it's a kind of a rare group with respect to what you find inside the galaxy cluster, which are more dense. So it's a good conservative approach. Objects which are within 50 kiloparsecs, like for example the Magellanic Clouds, I think they are like around 50 kiloparsecs. I may be wrong, but I think it's around that. They are merging with our galaxy. And Andromeda, okay, it's even at a higher distance, and one day we are going to be one galaxy. Perhaps that's a too optimistic case to generalize 2 million light years, but one could assume what we have in our local group, for example, with the Magellanic Clouds.
I was just saying that Magellanic Cloud should be within the virial radius of the Milky Way.
Yeah. So
on the contrary, Andromeda is not. So
true.
We would consider Andromeda a different object and not a Magellanic Cloud. Then here the discussion would be how would you define a companion and how would you define a satellite?
Good point. One should think more about this, I think.
So it is, I mean, maybe we should think about something like this. we can give a definition based on the dynamics, the potential well of the main galaxy, which is the dominating one. Let's see where in simulation, for instance, in embodied simulation, when particles are more bound to the higher mass object with respect to another, or I don't know. I would like to know what observers think about the observational point of view.
I feel like it really depends on your purpose, right? If you're, like you said, if you're looking at the observational property of the merger, you really want to see the tells and all the structures from the merger. But if you're from more simulation point of view, we can have this more solid criteria of when the halo entered the subhalo and how that happened. So I feel like it's hard to really generate a general criteria for how to define galaxy merger. I feel like it really depends on your purpose of the research.
Okay, let's hear something from someone that is not using GeoFinder. Anyone?
All right, we're going to ask people in turn. No, just kidding. That's what Marta will do.
Of course, one can think what is a merger, but what about like major and minor mergers? Like how small galaxy you can still consider a minor merger, for example? If you accrete a star cluster, is it a merger? This is like, I don't know, the heap of sand problem. Like a single grain of sand is not a pile, but if you add enough of them at some point, it changes.
Just a comment about the smallest minor merger. To my knowledge, the highest ratio between two galaxy minor merger is 470 to 1. I forgot the name of the galaxy, but that's the highest ratio of minor merger. Actually, of an AGN in a minor merger. I'm not sure about minor mergers without AGN, but that's an example of almost 500 times larger galaxy. And yeah.
Okay.
Any other thoughts on this?
I guess I don't know why we're asking this question, because obviously the definition of merger depends on what your science interest is. If I'm interested in binary black hole quasars, they're triggered by two major galaxy mergers, right? If you study galaxy dynamics, in which case the galaxy cluster has a lot of interactions between one another. If you go back to like intro galaxy class, you learn about morphology and irregular galaxies. Those are always formed from galaxy mergers, or you know, the heart-shaped galaxy that we learned in the intro astronomy. Or in other cases, there could be a perturbation from another smaller galaxy. You could have like RAM pressure stripping. I guess it just depends on what you do. And in my case, the most interesting galaxy mergers are those that trigger quasars, for example. I don't know. So in my short answer is there's definitely galaxy mergers.
Okay. Other comments on this?
Should we go on to the next question? I feel like we're spending a lot of time on the first one.
Go ahead.
So we heard a lot about the observable properties from the electromagnetic aspect of galaxy that's most likely to host YAGN or massive black hole binaries. So is there any thoughts on this? Like, especially I want to hear about from observers, what observational properties that interest you the most, or is the most relevant to your research? Like, if you, what's the band, or what's the like the properties basically, because I'm not that familiar with observations, so I really want to know like what's people's ideas, especially observers, on this topic.
Well, there have been some recent works looking for dual AGN using infrared observations. But again, they used WISE telescope. It's work by Satyapal and Feifle from a few years ago. But the problem is WISE doesn't have really good angular resolution. So they were only limited to large nearby galaxies, but they can resolve actually two separate infrared sources. People use X-rays also. Again, problem with resolution. Chandra is a lot better than WISE in terms of resolution, but still, at larger distances, you can't resolve two X-ray sources. There are also some Bayesian packages. I think Eddie Ford is developing those. Baymax that are used to statistically estimate if a source that appears as a point source in Chandra is actually dual. Actually two sources that cannot be resolved with Chandra. Another aspect is people use spectra, looking for double peak lines as an evidence of dual AGN, but there are many other factors that can cause double peak lines, such as certain geometry in the nucleus of the galaxy. And I see lots of works using double peak lines, detecting very rich populations of dual AGN, but I would assume that most of them are not actual dual AGN, and those double peak line profiles are just caused by some other factors within the galaxy.
Any other thoughts?
So, David, what do you think about?
Well, I'm not an observer, but I mean, I think that star formation rate should be a good tracer for dual AGNs, right? Because the galaxies just merge, right? So you have two massive black holes very far away at kiloparsec scales. So the bars of star formation probably is still ongoing, right? So it would be basically a good tracer for massive black hole dual mass AGNs. Whereas for massive black hole binaries, I'm not so sure, because I mean, massive black hole binaries are objects which are actually really, really close, right? They are subparsec scales, 10 to the -3, right? So that you need to have dynamical friction, hardening, so on and so forth to reach these scales. So the time elapsed between the galaxy merger and actually the detection of massive black hole binary is so large that basically any star formation rate bars is basically vanished, right? So for dual AGNs, for me, I would go for bars of the star formation rate, but for massive black hole binaries, I'm not sure what observable properties. For me, there are not really. At least for now, there is no good tracer for this. This is my impression.
I mean, I raised my hand before David talked, so essentially, I was going to say the same thing. So yeah, I guess that it's a matter of, I mean, in terms of massive black hole binaries, it's a matter of finding out which galaxies have black hole first, to characterize the occupation fraction, then which galaxies tend to merge more, and then on the other hand to characterize the delay between the galaxy merger and the black hole merger. So how correlated are the properties of massive black hole binary hosts with the properties of galaxy merger depends on this delay, but of course there's lots of theoretical uncertainties here. So yeah, I think that's, I would say that's kind of the summary.
It's a cardio for me.
So, I mean, which galaxies tend to be more involved in mergers? I mean, I would expect, for example, more massive galaxies to be engaged in more mergers and low mass galaxies. So in that case, yeah, exactly. So, yeah, I mean, in this case, you'll be biased for, I mean, you preferentially find high mass ratio.
I want to say something related to Marco's point, that there are some people that believe in the photometry to classify dual AGN. Probably we could study the morphology through photometry of those systems that are classified, and then understand if there is a relation between the morphology. So if we see spiral galaxies or elliptical one, to understand if they are dual or not.
This is a good point, the morphology, but the issue is that I think, I mean, how far can you go to with, I mean, images, right? Because you need the images, right, of the galaxy to say, okay, this is spiral or this is a elliptical galaxy, right? But how far, I mean, you can reach with photometry, right? I mean, you can reach, for instance, up to redshift 1, 2, 3. I mean, because for LISA, probably high redshift is the more important thing. For PTAs, for instance, in massive black hole binaries, you are basically low redshift, so probably the morphology is a good tracer, right? Because you can actually go up to redshift 1, which are the massive black hole binaries in PTA band. But for LISA, I mean, I don't know the morphology. I mean, maybe it's a little bit challenging, especially for high redshift. But yeah, I agree that morphology is, I mean, could be a good tracer of this.
I'm not a black hole binary person, but is there also maybe, we're seeing these in these post-merger galaxies, and so we assume that at least a higher fraction of them are going through a starburst than what we would expect, or I don't know if the timelines work out on that, but could we look for not just sort of the morphology of a merger remnant, but also a starburst or post-starburst stellar population where you have this older stellar population plus more recent star formation? Maybe that would be an avenue.
Regarding the morphology of how far you can go, there's a paper from this year. They use HST data and they study the morphology of the host galaxy of a dual AGN, a redshift 2 something, if I'm not mistaken. And I mean, it also depends on what you use. For example, if you use GWC, then you can go farther. If you use something else, then you cannot see anything. If you use, I don't know, some millimeter, then you need to have gas. So it's more of a question of what kind of galaxy you think is hosting your duals, and then you can try and see, I don't know, like tidals, morphological features like that. But then I have a question for all of you. Why are we thinking about looking for dual AGN depending on the galaxy? I mean, it's, in my mind at least, it's easier to find possibly double-peaked AGN, like it's with the GMP with Gaia, the vastrometry technique, than like saying, okay, we have this galaxy, does it have a dual AGN? Because then if you have a dual AGN with after a merger or whatever, then I would expect that those two black holes are accreting so that I can kind of see them, depending on how obscured they are. Also, then it depends on the band and all, but maybe it's more of an issue on the AGN side and on the galaxy side.
Okay, so maybe I can ask which signature can we look for finding AGN instead of, I don't know, random stuff in galactic nuclei? Is there something that can be associated unambiguously with binary, or should we just wait gravitational waves? Yes.
I mean, X-rays are the best, because, I mean, if you have, like, if you have X-ray emission from 2-point sources, then you can see if the spectra has like the expected power. Pardon? Depending on the counts, yes, that's also the point, because and also the resolution, because, for example, maybe you have a coverage with Chandra, but then you have to also consider how the PSF is and what's the shape, and then if the PSF is elongated on the other way, then you can say, okay, this elongated shape is real, otherwise it is not. So it's, I mean, my answer would be X-rays, but we need a better telescope than what we have so far. So.
With a larger area, which is impossible. So in order to do this kind of studies, we need Chandra, again, with a slightly larger area, which is impossible. So no, I mean, you need better mirrors. And the mirrors of Chandra are unrepeatable at the moment for several reasons. So the resolution, the angular resolution that you can reach with Chandra, and it's sad to say so, is excellent. But the point here is, if we cannot repeat the same exercise that was done with Chandra, with the mirrors that were then put in orbit on the Chandra facilities, then we are not going to have this angular resolution anymore in any X-ray telescope. As sad as it sounds, that's a reality. There was links, but I fear that it's not going to happen. I'm not sure with what is the status of links, but links was meant to be the successor of Chandra. But as far as I know, Chandra can reach angular resolution that are comparable to HSD. 0.5 seconds. You can do some tricks. Sub-binning resolution. I mean, you have experts here, but this is not an exercise that is repeatable unless there is some agency that can, I don't know, throw money on it. But
I'm not an expert, so maybe it's a naive question. And what about axis? Is
well,
going to
as I said,
happen?
it depends on the science case, right? Do you want spectral resolution? Do you want a calorimeter, or do you want angular resolution? Or you want area? All these things do not go in parallel, hand to hand, because the blanket is short. If you want something better, you cannot. Yes, it's impossible. But from an actual technological point of view, is not. So axis, I'm not an expert on axis, so I need to look at the specifics. But if we want,
it's an almost X-ray observatory is founded by.
What is axis?
NASA, I don't know.
Yeah.
So it's something going to be submitted now, basically as a NASA probe. It's supposed to be effective area 10 times better than Chandra at the launch of Chandra, not Chandra now, because Chandra now at 1 keV has no area because of the dust and or whatever ice deposition on the AC skimmer, with the 0.3 arc second resolution. So for this kind of analysis should be good, provided that the mirror is no, spectral resolution is just like ACES. Sorry, no, 0.3 arc seconds resolution. And no, just wait, it will come back in a second. And what I wanted to say, I forgot what I was talking. No, it was about access. But so far I have not really seen any proof that mirror can be done within $1 billion. I mean, the whole mission, I've not seen an actual proof that can be done. But the proposal will be submitted in a couple of weeks from now to NASA, so we will see it.
Okay, so X-ray seems to be the signature to look for. Okay. So what about other periodicities in the GN curve? Do you think that they are probably riskier? And okay, Massimo, maybe you can enter here since you suggested that question. What if? Yes, you did.
So I guess that you were previously referring to pairs, large-scale separations between the two black holes. Of course, in this case, you're referring to binaries.
Yes.
As a matter of fact, closed binaries, if you want to see the periodicities to be shorter than 1 year. My personal, so I saw, the reason why I proposed this question is that I know that a lot of people are searching for periodicities in AGN in order to try to find binaries. There are theoretical reasons for it. There are one of the issues is that AGN are varying objects with a red power spectrum. So if you see only 1 or 2 fluctuations, you cannot actually prove that is a periodicity. And there is the proposal that maybe with LSST or possibly Roman, you could detect systems with significantly shorter periodicities in order to be sure. My point is, I'm not completely convinced that even if you see 50 cycles, that is a unique proof that it is a binary. What if it is something real? There's some physical reasons for the periodicity that has nothing to do with the binary. We heard yesterday, for example, could be that you're observing some observational features due to the helicoidal shape of the magnetic field in the jet. And many of these systems have been selected through gamma observations. So we know they are blazars, a sizable fraction of them. So my question is, would anyone be convinced that the 5 systems that will be selected by LSST having a periodicity of 1 week are actually binaries or not?
So, first of all, I think you're right that there are some degeneracy between AGN periodicity in AGN light curve and what kind of science we're studying. So that's why I guess as a young person, I'm open to multi-wavelength observations in order to have more robust or find the smoking gun evidence that something is a binary. But then I think so far, just from the periodicity alone, it's very hard. But also we have to consider different timescale of things, different transients that could come from AGNs. Like the talk we heard in the past 2 days, I guess there's different events like QPEs, TDEs, I guess also TPE, tidal peaking events that could produce different kind of periodicity. But they're all in different time scale, I guess. The answer is we need, I guess, more theoretical models along with observations to know. Hopefully in the near future, but if not, then gravitational waves should tell us some information. That's why it's important to figure out merger rates, for example, in LISA, in the case of massive black hole. But also in terms of, so I'm talking about compact binaries, right? So that's the regime that you're talking about. Like in LSST, we have 10 years of data, and they're taking every week. If you have some binaries with period of a few days or up to a month, then maybe it's possible to identify some kind of periodicity, but you're saying that might not be enough to confirm, and I totally agree. Yes, but even for the case of dual AGN, I think we're constraining the theoretical model along with more observations. So other people might be more familiar with this. So I also still want to address that multi-wavelengths is important. Like JWST recently discovered 17 dual AGNs up to high redshifts. And they already constrained the cosmological model by a factor of 2 or something. We already observe like 2 times more than what we predict from cosmological simulation in the early universe. And those dual AGN candidates are, I guess, cross-confirmed with the infrared information. So I think we could definitely make use multi-wavelength info.
I agree with you, of course, and I'm a strong proposer. I push toward theoretical works that make actual observational predictions for different features that have not been observed yet. I totally agree with that. And I was wondering whether you can elaborate more about the possible multi-wavelength observations that could discriminate between a binary scenario, an helicoidal jet, a precessing jet, or whatever thing we didn't come up with yet.
You mean about binary or just
about closed period binary?
I think binary, in terms of binary, I don't see a lot of observation or theoretical paper on jet feature. Some people, there are a few theoretical papers that produce binary jets could produce a corkscrew-shaped jets, and they have a theoretical prediction on the light curve as well, which is probably in X-ray. Yeah, and I think the period of variation of at least from the theoretical prediction depends on what separation you have, a mass ratio, that kind of stuff. But it's
if it is a binary,
if it is binary, it should trace the orbital period of the binary in general. But again, it depends on the jet alignment, what kind of angle the binary has, and yeah. I don't remember too clearly what the result is, but there is some way to indicate the orbital separation.
But just to give a counterexample, for example, what if we have an inner region of the accretion disk like the one that have been discussed today, that is hotter, sufficiently hot in order to be geometrically thick, and therefore being slightly misaligned because of whatever reason, it precesses like a solid body. And let us assume that the jet is perpendicular to the disk instead of the spin. So that would precess, the frequency of the precession would depend on the outer radius of the thick part of the accretion disk, right? And that is a free parameter of the model. So if you're asking which kind of periodicities are you expecting, if you have a periodicity of 1 year, we can explain it with a given radius. If you have a periodicity of 1 day, it's fine as well, as long as you do not go too close to the horizon. But in such a case, a binary wouldn't explain the system anyway. So it is not immediately straightforward from pure, even multi-wavelength, but photometrical data, in my opinion. That's I was wondering whether someone of the young people can come up with a nice prediction that is not if you want, let us put it as an invitation for you. If any of you manage to come up with an idea and meet together, please write a paper and enlighten the community so that we know what to search for.
I guess you can look at big populations of quasars and see if there's any correlation between optical UV X-ray in that case for most quasars.
But the systems that have been proposed do have, but indeed, most of them being blazar, of course, since the emission is dominated by the jet at all the frequencies up to down to radio, they vary consistently, of course.
Okay, I should stop talking.
But thanks a lot.
Okay. So let's go ahead in 15 years, and let's see. We have. Let's assume that we have LISA observation. Then, what we can do?
No, I have no idea. I mean, so my question was actually heretical. So suppose you have LISA flight, which will be, and you observe a gravitational wave. So you have an uncertainty on the sky, which is a few. We have learned from David, right? That we will have an uncertainty on the sky, which is as large as a few degrees square. What would be the plan to find the host counterpart?
Then I can see that also Chiana has something to say.
Do you want to say something?
No, go ahead.
No, I mean, I think there is no plan, as far as I know. So that's a big issue. Yeah. I mean, there will be the good synergy between Athena and yeah, that's the problem. Now Athena is not.
The problem is that the time scales are different.
Exactly.
LISA will fly, while Athena will be still probably on the ground safely in a building being built in some clean room. I don't know.
Yeah.
I mean, there is no plan. So Athena has a different time scale from LISA, from what I know. But please correct me if I'm wrong. If anyone. It's not even. Yeah, it's not even adopted yet. So, boop, and. It's 2035. Forget it. Yeah, forget it. They say 2035 if it's adopted now, but Athena.
Okay, let me explain this. So for Athena, there is one step that was not done for LISA, which is the feasibility. For Athena, the feasibility was done, not visibility, but feasibility. And because of this, should be adopted, there will be a fast production process because the mission has not stopped. ESA has stopped, but the mission is still going. The consortia are still working. So when it will be adopted, there will be a faster production and launch. So the goal is to launch by 2037. Should everything will be all right. Regarding LISA, perhaps it's supposed to be launched earlier, but this feasibility exercise, including the costs, that was done very, very carefully for Athena, and especially for the new Athena, which will be proposed to ESA basically now, because the new science redefinition team has decided Athena is still flagship. This was not done, so I would be surprised if LISA fly in 2035 or so. So I think that perhaps that can be launched together. Maybe there would be a year different or two, but I think they could be quasi-simultaneous if ESA wish. So I think it's everything in the hands of ESA right now.
Okay.
Yes, so I guess that probably my hope is that we can identify some kind of transit event that can be more unequivocally linked to mergers. So yeah, probably there are like many that have been proposed in the literature, especially from simulations. Yeah, whether that is the disappearance of hot mini disk leading to a decrease in the hard X-ray emission, or whatever the other features. So I guess that probably I don't know, a transient service will be very important for this. And yeah, also I think Chen made a very good point with the gravitational waves. So I think that probably part of the hope is that we can characterize merger at least binary signatures combining PTA information and electromagnetic variability, correlate the two in some way, and find out something before LISA flies.
Yeah, I mean, I agree, but also, I mean, the good thing is like the error box of LISA shrinks when we approach to merger, right? So probably at merger time, the sky localization is not so big enough, so big that we can actually have just 10, 20 galaxies, so maybe we can do follow-ups. But still, I mean, depends a lot in redshift, in what is the mass of the massive black hole binary, so, but at merger should be kind of doable at low redshift at least. Look one by one the galaxies in the LISA sky localization, because you have also constrained the redshift, let's say the luminosity distance. So it's, could be, I don't know.
So, regarding finding, because the idea would be also to be able, hopefully, to find, to localize a LISA source electromagnetically before the merger, because then if you manage to observe the merger in electromagnetic waves and gravitational waves, that would be so much better. Something that was, I think, written in the LISA white paper at some point is that, in principle, since LSST has a pretty wide field of view, then you can basically tile up the localization box of LISA, maybe even multiple times, to look for signatures like the ones that were mentioned. And at that point, if you find like a region, a galaxy that is a particularly interesting candidate, you can follow up with better resolution observatories. But of course, it's going to be a difficult exercise. And I think, at least in my perspective, I'm not probably I'm far from being the most expert on this. But the problem is that we still have kind of not so clear idea of what the merger signatures of LISA binaries in the electromagnetic band look like. And I think that's what we really need to work on.
I was going to mention the exact same thing. I guess by the time that LISA flies, we would already have 10 years of LSST data. So if we believe that binary black holes are periodic quasars, then that's a very robust, I guess. And as you said, as we get more cycles of gravitational wave, the error bar is smaller and smaller, right? So ideally, LSST would observe up to hundreds of millions of quasars. But if it also depends on the chirp mass of the binary and how many gravitational cycles you get. You could get down to, it's actually an analysis that I can talk to you more about. You can get down to a few thousand or a few hundred sources. But one problem is exactly how does the periodicity actually looks like. So if we assume like sinusoidal periodicity, that's a very easy first order approximation, giving some error from gravitational wave. But if you assume some other periodicity, I guess it's another small detail, but that could change things. But another more major I guess gray area is the intrinsic quasar variability. Some people believe that that could produce some kind of periodicity to mimic the true binary black hole signature. But I think the current state is just from the noise, the red noise alone, you cannot produce the true variability for more than 10 cycles. So with 10 years of LSST observation, I think it could be promising that we could identify. But that's only given the gravitational wave information. Otherwise, the error box has too many quasars. Yeah.
And for identifying with LISA sources, as alluded to, there's been some recent work, and I think the paper was brought up yesterday as well, for the mini disks and this decoupling I talked about in the morning. That if they're accreting, you're getting X-rays from the mini disks, but when they decouple, the mini disks disappear quite quickly. It's a very short lead time. It's order hours prior to merger, but you lose the X-rays. But then they actually, if you get a kick, they come back. So X-rays disappear, merge, but then if you kick, it drives a spiral shock into the disk, and then you might get the X-rays back. So that's a possibility if you kind of know where to look.
Of course, this is a clear-cut prediction, I would say, but there's been quite discussion since the first time it was proposed, due to the fact that it's unclear. So if you deposit the energy mostly where most of the mass of the circumbinary disk is, it depends how much time it takes to reach the photosphere of the circumbinary disk and then to be emitted. And if you deposit in the center, you expect it to thermalize. So that it is not clear at all, in my personal opinion, whether it will be in X-rays or in infrared if it thermalizes. Would be bright in infrared at that point, but yeah, exactly. And then you rebright at in different bands possibly.
And when we do these simulations, we set them up so that these things are in steady state and they're accreting and whatnot. But I don't think it's 100% certain that binaries are accreting at rates that are comparable to single black hole counterparts. They might be much dimmer. So you might have situations where they're actually dark, like they're carving this cavity and stuff's building up at the wall, like this old picture from the 90s. I don't think it's totally gone necessarily. So then maybe you merge, and then you might actually get an AGN that turns on after merger as material that's built up in the disk kind of flows in at the single black hole then. Because you can have different thermodynamic conditions and things that can actually shut off these streams and the formation of mini disks, and you can just have black holes that are just this blender in the middle of a disk that aren't actually being fed if you don't set your situation up to be nicely near a steady state configuration or something. that might be a bleak picture where you don't have precursors and you only have a bright thing that turns on at the very end after merger.
Okay. Any other comments on this? Okay. So maybe you can slightly move to the final part of the discussion, maybe a bit more focus on modelization of massive black hole binary evolution. So what do you think is the most compelling process to model in this long evolution? So we have to improve our modelization of the first phase, so the pairing, or when the binary forms, or I don't know, the finally spiral where probably there are some multi-messenger aspects. What do you think?
Like I said in my talk, I find that it's most like the nuclear friction is the most kind of the bottleneck and dominate the decay process. But I find that in most of the simulation, like catch you it's the embody, so there's not necessarily gas component included. So I guess I really want to know like what's people's opinion on this, like how is there any way that we can really focus more on the gas component of this, or like because I guess my question is just like for the catchy people, like is there any way that you can talk more, elaborate more on the gas part of the
I was going to say something, but I think you and Christian and Jessica, I don't know.
No, go ahead, go ahead.
Yeah, I was going to post exactly what was said like during the past 30 seconds.
Well, I was going to say that I think all processes, especially if we talk about multi-messenger and we care about how gravitational waves and the electromagnetic radiation kind of work together, we need to improve all stages. In terms of gas and Ketchy, we have some hydrodynamical simulations, but I think as like Christopher said, how exactly the circumbinary disk evolves and what the properties, like what's the metallicity in that disk, temperature profiles, like what's the structure of the magnetic field. There's so many really complicated processes that kind of all work together, and then like do the black holes detach? Then if you get a kick and the black hole moves away from the circumbinary, does it move through the circumbinary? Like I think the parameter space and the physical processes that go inside evolving, let alone like building a model, a subgrid model to put in a hydro simulation, I think the complexity is insane. So like it's something I also find really difficult, how to combine all these different tools we have in the theoretical aspect, because like for resolution and time and computational cost reasons, you cannot have all these processes, even though there are now papers that increase resolution a lot around the black hole all the way down to the accretion disk, but there's still a lot of way to go until we capture all processes to be able to then get an SED of that AGN and be able to then compare with observers. And what happens with the dust is there's a torus around this structure to have corona, like the really complicated structure, I'm sure you all know, and trying to put one component at a time there by hand and see what the simulation will do, how the feedback will couple. It's, yeah, it's difficult.
Yeah, I mean, because you mentioned the sinking and dynamical friction phase before that, right? And there are studies who that find that the detailed structure of the interstellar medium plays a role for that. Like if you have it clumpy, the sinking timescales are totally different compared to something that is more smooth, spherical, symmetric. So already there we are missing a lot. Then Dimi has mentioned a lot of processes that cause a lot of trouble on small scale. So I think we have to be honest, from cosmological simulations, you can't expect any solid predictions for merger rates, occupation fractions, all these kind of things. So I think there's a lot of work to be done, and I would not trust the details of any of this at the moment too much, right? Because we also know that there's a lot of intrinsic scatter in the evolution of multiple systems. Sure, maybe this goes down if you include more physics processes, but it's a mess, I think.
I completely agree. It's messy, and like with regards to the gas and the interstellar medium, like it does make a massive difference because also many of your physical modeling and your subgrid stuff is stochastic, like star formation. Depending on what your mass ratio is between your stars and your black holes, just forming a star, like, you know, a fraction of a parsec differently, like it changes everything. It can change your, like we have a colleague who's done some studies, like he found moving one star like kiloparsecs away from the black hole, it changes the evolution. It changes the merger timescales. And I'm not talking by like a couple of mega years, by like giga years. It's chaotic, it's stochastic. Like you need to do this in a statistical way. And I think that like we're never, like everything is stochastic, and like you were talking about gas, like it does make a difference, but I think it makes more of a difference because like the distribution of your gas dictates where your stars are. That's why I think we don't bother too much modeling the interaction between gas and the black holes necessarily, but like because also the gas is like it should be softened, right? It's not particles. So yeah, everything is stochastic. So I think you need to be really careful making kind of hard predictions from these things. I think everything needs to be a distribution considering like all of the uncertainties in the modeling of your interstellar medium and star formation and everything.
No, I agree. I mean, I just wanted to bring another aspect into the discussion, which is, from my perspective, the seeding. At least if you worry about like predictions for mergers, which I think are absolutely not constrained, and cosmological simulations make wild assumptions there and can't really follow the dynamics afterwards. So yeah, a lot of high redshift problems as well.
Yeah, the comments. Oh.
Yeah, like without entering the details, so regarding all that has been discussed, I wanted to kind of raise a more like philosophical point, which is, so how far do we want to go in terms of subgrid modeling? Because, okay, if we just have like simple physics of hydrodynamics plus gravity, then everything is, well, kind of more deterministic. It's, you can derive things ab initio, well, yeah, whatever, ab initio. As soon as you start adding subgrid models, then, well, the first thing, you make your models more complex. So then they're less analytically tractable. It's more difficult to link the first principles to the results. And then, of course, you have to calibrate your models in some way. And as you calibrate your models, you lose predictive power, because you're, by definition, if you want to calibrate a model, you have to incorporate some kind of observable or some kind of observations. So yeah, of course, if you include a model, you will have free parameters and you have to tune them in some way. So yeah, you lose predictive power. That's what I want to say. So, so then, yeah, I mean, of course, we can make our simulations as complex as we want. We can introduce lots of subgrid models and turn them into some kind of like specially resolved semi-analytic models. But where should we stop? That's kind of the question.
But if you don't have any subgrid models, for example, like how would you suggest doing star formation? Like
No, of course they're necessary. But
okay.
I mean, you can always add more and more subgrid models, because by definition you're always missing some physics. I mean, you have many processes that are like depend on multiple scales, so you're always going to be missing something. I mean, you can include something else, you can include cosmic rays, you can include, but there's always going to be something missing, right? So it's like, yeah, the question maybe is like, should we stop at some point, or is it always good to be adding subgrid models? I'm not arguing for stopping. I mean, I'm just like raising the question to see what people think. Um,
Let's pretend we
I
are
mean, it's not really a philosophical question because I think it really has implications in what we do. I mean, it's more like a methodological question.
So my point is that if it is just a philosophical question and we have infinite power, infinite computational power, never.
No,
every time you have a new way to model sufficiently well physics, you put it in.
Okay, so it's not just a philosophical question. It's more like a methodological question, but it's difficult to answer just with. I mean, you have to put something, some personal preference into it. Because, I mean, for example, if you want to include many feedback mechanisms, by definition, you're going to have some degeneracy. You're going to have, well, not by definition, but you're going to have some degeneracy because you are going to have several mechanisms that can do several things. So then it's going to be more difficult to calibrate the models. And in order to calibrate the models, you will have to bring in more observables to calibrate them. So then you make your model, your simulation model as a whole less predictive, because you reproduce, by definition, the observables, right? Because you're tuning some parameters so that you reproduce it. In every model, you have some kind of free parameters, that is the amount of, in AGM feedback, typically some efficiency parameter of what fraction goes into thermal feedback or into kinetic feedback, whatever. So that's kind of, I mean, of course, there are two limits that are, either of them is not good. I mean, if you don't put any subgrid physics, it's bad. If you include any possible subgrid physics, then you're not really doing a simulation. So, yeah.
I mean, I don't know if you need an answer about this because I share your concern, but I think the main problem is that here, in reality, it depends on what we are looking for. And so you would be more interested in some physical process with respect to something else, depending on the scales involved, the masses, the resolution, the process that we are studying. But in principle, when we will have quantum computers in whatever hardware store, maybe we could tune perfectly. Maybe we wouldn't even have necessity to implement a subgrid physics. So from fundamental physics, we can reproduce jets and dynamical friction. So, and then we will simulate the universe.
I would say I'm an advocate for subgrid models. I would say, for example, you can get the correct answer if, depending on what you're looking for the wrong reasons. For example, like if you want to produce the correct outflow rates and the correct star formation rates of galaxies, you can use supernova feedback only. You don't need photoionization, for example. However, if you start actually looking about other things, like some of the small scale stuff, like the star clusters and things like this, is wrong if you don't have photoionization. It's not correct. It's self-regulating. Supernovae will do the job for photoionization if you want to. And many cosmological simulations and many other simulations still do not use photoionization, even though it's been proven that it's wrong, because they just say like, oh yeah, but we just care about the global properties of galaxies. So, okay, if they care about that, that's fine, but at the end of the day, if you have a physical process that you know exists in the universe, like, you should try and model it. I think you should recalibrate every time. You should go back to all of your subgrid models every single time you add something new. You can't just keep compounding them, right? You have to go back and be like, okay, now we need to look into this process and see if we're modeling it correctly, especially when you start to push resolution. You need to also change your subgrid models. Sometimes something that was calibrated on kiloparsec scales doesn't work anymore, that you have sub-parsec resolution. So I think, like, I'm in favor of adding as much physics as possible, as long as you fully understand what you're doing and you are kind of also like using it for the problem that you're looking at. But I think people that neglect it because they match some kind of like global properties and then start to look at, say, small scale properties and make statements on that, it's like you're not making a prediction anymore for something, like you're missing processes that are important. And like you need subgrid models to do all of that kind of that kind of stuff. So I think depending on how deep you want to go, you just keep adding subgrid models as long as you understand what you're doing, I guess. Maybe none of us understand what we're doing.
Of course, like first thing is that what you actually want to model, but the second thing is like at which moment to stop adding stuff at the bottom. I think the key thing is that whether the scale you want to add is coupled as a I don't know, back reaction cycle to the larger scale. So for example, in galaxy simulations, I don't know whether it doesn't make sense to include a subgrid model which has I don't know, single planets or moons, but single stars make a difference because of course, well, star formation and feedback to larger scales. So, and of course, another example what Jesse said, for example, in my work, for example, ignoring post-Newtonian corrections can actually compensate your missing background modeling from, let's say, from the relaxation effects of your star cluster. So you can easily end up having a correct result for completely wrong reasons, completely different physics. And that's why you, as you said, you really have to understand what you are doing and not just use these models as I don't know, black box switches to get a correct result.
Okay, so if we can quickly summarize since we meet the hour. So apparently we don't have any plan to deal with LISA detection, so we need to work on this. There is a lot of job to do for massive black hole binary modeling, second plan. So I don't know, probably we need to tell the funding agency that this science is timely. Joking. And okay, so thanks a lot for the lively discussion, and thanks to all the speakers of the day, and thanks to you.